Okay, hello everybody. So we are back in the Grayscale School for a bit of Sycl on GPU, and this afternoon we will have also a bit of Fortran on GPU. So, David, it's yours.
Thanks, welcome. For those who followed the Sycl for CPU last week, so we're doing the same now for GPU. I put on the Sycl course channel on the j'ai une absence. On Discord, yeah, on Discord, on the channel Sycl course. I put the names of the Git repositories to be cloned. In the GPU one, so you need, as usual, you need the setup and the GPU one, especially because the GPU one for the practice is using the CMake files, which are given in the setup. If you want to have the slides live, you have them in the Sycl for in the GPU repository in the slides subdirectory. And so let's go with a few reminders for those who followed the Thursday webinar, but perhaps new for the others. So a few information about how to use Sycl for GPU, and only focusing on the information that will be needed for the practice. So first point, when doing a Sycl program, you should create a queue, one queue by device. So in this practice, we are doing simply one queue. So now for GPU. So last week, we were seeing just a queue with the CPU selector, but as you see now, actually, you can select any kind of device. So if you say nothing when you're creating your queue, you will have the default, the same as if you say default selector. So there's a kind of runtime selection of what is the best device. So we could discuss a lot what is the best. So quite often it depends on the implementation you're using. Quite strangely, when you implement with an Intel implementation of Sycl, the Intel GPU has a good rank. But generally, if you have a discrete GPU on your machine, it will be the default choice. So if you say nothing, and if there's a GPU in your machine, it will try to run on GPU. So you must be aware of this. If you want to enforce a CPU, you say CPU selector. If you want to enforce a GPU, you may say a GPU selector. But actually, you may do something very complex because Sycl gives you much information on the available device at runtime. And you can write your own selector, so to make a complex mix, looking at all the information and the characteristics you can get about the device to choose the one you prefer. There, I'm doing. So as usual, you make it with a lambda on the fly. So there, I'm creating a queue with a lambda, which will select a given device. There, I have an example where I'm looking at a Boolean, and if this Boolean is true for Arc CPU, I will return the same as the CPU selector. And if I have this Boolean, this test on Arc GPU true, I will return the same thing on the GPU selector. But you can also make a complete fix thing using the information. For example, in this display, I'm showing that I can display the device name, the device vendor. But if you look at the reference about Sycl, you'll see that there are many information, the number of streams, whatever you can imagine. And you can, there's way also to say, okay, I want something when there is NVIDIA in the name, whatever you want. So first point, make the queue. I focus a little on this because it's in the genetic of Sycl to be able to be run anywhere, discover what is the device, what are the devices available, and try to choose the best one at the runtime. So the typical way, as we said last week, the original way to do computations with Sycl is to use buffers and accessors. So first you create buffers on top of your input data, your arrays, your whatever. Then you submit a job on the queue, which will be forwarded to the device. And then in this first step, you are creating accessors connected to the buffers. So the new things with accessors as compared to the buffer is that that's the place where you say, for this task, I will be read-only or write-only or both on all these sort of buffers. So that's the place where you give information to the system about who will read, who will write, where. So this first submission is made with a lambda, as usual, but this lambda is capturing by reference because until this point, we are still running on the host. We are not yet on the device. What we call usually the kernel in the GPU world, it's this CGH parallel 4. So that's where I'm submitting a new lambda, which is a kernel. This one eventually captures some values by some data by value because they will be duplicated on the device. And that's the kernel. There, I'm just doing a square of my input. And so you see, I access the data through the accessors, but I use them as the usual arrays finally. So the kernel is just this lambda, this internal lambda, capturing by value. If I want to look at the result outside of this computing, I will use this host accessor there, which is specific. It's when I want to access the data on the host side. And there I'm doing so this accessor on the output buff and just displaying the value there. The key thing also with buffers on accessors is that because you say who is writing, who is reading, the runtime organized for you what is done in which order. You don't need to mind about doing some weights there and there to be sure that the work is finished. In this specific example, when arriving on the host accessor will wait until what is done before on the queue is finished. And also, once you have done the buffer, remember that you should not access directly your initial input or output until the buffers have been destructed and give you back the end on your original arrays. So that's with buffer accessors. We have seen last week with CPU that actually we may use row pointers, so why not? I'm not doing any buffer, accessor, etc. Just using directly my pointers there in my kernel. Because I don't use, you will notice also there's a shortcut. There I'm first doing submit, then accessors, then parallel 4 on the handler, which I received there. I have 2 levels of lambda. If I do not need to make some accessors, there is a shortcut. I can directly call the parallel 4 on the queue. That's what I'm doing there. I'm doing directly in one step queue parallel 4 because I don't need the intermediary level where I was making the accessor before. Because there's no buffers, I should do a wait before I'm doing the print on my output. But this actually on the GPU will not work. It was okay for CPU, but on GPU, it will not work because my row pointers, they make sense when you are in the host code, but once on the device, they are not valid anymore. So there's a way to make these simple kind of things if you don't want to make buffers, accessors, etc. There's a way, which is to use malloc shared. So there I was just doing a new, usual new in C++. Instead, I will do a malloc shared of float with a size. This malloc shared is attached to a given queue. You will notice this queue argument there at the end. And this will return something which looks like a pointer, a float star there, but which is usable both in the host code and in the GPU code. And what happens behind the scene is that I do not need to make any copy. Actually, it's somewhere at the system level that when the GPU needs something and use a pointer, it will trigger some kind of triggering some kind of copy because the system will notice, we lack the data, I will copy it. And if I use that same pointers, in some host code and use it, he will see that, oh, I need some data which were modified on the device. I take it back on the host, etc. And so all of this, that's what they call in Sycl the unified shared memory. All of this is happening at some system level and you don't care. It's automatic. So it's easy, very easy to create and use. And automatic, but as you will see in the practice, because it's so automatic, it's perhaps not the most efficient way. So that's what I call the easy, lazy way. Easy to write, not so efficient as it could be. It's potentially slower than using the buffers and accessors because this system lacks the information who read, who write, when, so improvise on the fly. So that's the shared memory, but you can push a little more in the control we take on anything, which is to use instead the malloc device. If you instead of the malloc shared, you are doing a malloc device, you are creating a pointer and a memory area which is only usable on the device, not on the host. And then you need more work. You need to explicitly copy data in it yourself. Instead of relying on the unified shared memory, which is automatic, you know what you do, and it's your job to do the copy. And that's normally the way you can be the more efficient because you know your problem, which steps are done at which moment, and so you do the copy, you do the malloc, and also you do the wait at the right moment. So for example, there, I'm doing my two input-output arrays on the device. There, I'm calling on the queue. Instead of submit, I'm doing a mem copy, saying, take this, it's the size, the reverse size, I think. Take this input on my host, put it on the device input, the one I just created with the malloc device before. I give a size. There's another way to write it. I think in the practice we use the other one. This one is mimicking the C function. You give first the target, then the source, then the total size in bytes. You see I multiplied the size of my array by the size of a float. I realize now that there's a simpler one, which I use in the practice, where you say from, to, and the number of elements. And it is computing in the C++ way the size. Okay, so you're doing explicitly the copy, then I'm submitting my kernel, then I wait, and then I'm doing the copy back of the output on my host machine. So this one, in theory, is the most efficient, but you do all the work. You do the creation of areas, either host or device, you do the copy, you do the wait, and you hopefully should not make any error or you will not get the expected result. Sometimes when you are doing things one after the others, rather than saying wait after each thing you are doing to the queue, you see there, I have a wait there, I have a wait there, I have a wait at the end. Instead, you can do a queue where you say it's in a queue in order, meaning that whatever you submit to the queue will be done in the same order with an implicit wait before each step. It's not the default. The default is that if I ask many things to my queue, it may be run in parallel. So if you want this, if you are doing something quite simple, you rather use a queue in order and then it's okay. It's okay, but the only things which are in order are the things which are sent to the queue. So if at a moment you want to do something on the host, and the host need that whatever has been done on the queue should be finished, even if the queue is in order, it's not sufficient. You will need to add a wait before doing what was doing the host accessor before. Because the queue is in order, but if you do something in the host, you don't know what is the status of your queue. So don't think I put a queue in order and everything is automatic and okay because it will be done in the order I write it. It's only true for what is submitted to the queue. not what is happening on the host. There's a trap there. If you want to do something a lot more complex, we'll try to do one at the end of the practice. Actually, you should notice that when you are doing a queue memcopy, a queue submit of whatever, when you put something to be done, a task on the queue, in exchange, it is returning you an event, a cycle event. In all the example before, I was just ignoring this or calling directly queue wait after it. But actually, the function returns something, which is an event. And the event is the object that is able to say to you, I am finished or not. And it's also the object on which you call wait when you want to wait on the event. And sometimes you need to do some complex task graph. And not only you can use the event to say wait, but you can use the event in another submission to the queue saying you must wait for these events to be finished. There are prerequisites to be done before you start. So there, and again, you do this at the same place where we were doing the accessors between the submit and the actual action, kernel action. So for example, there, you see I'm doing memcopy, which return me this E1 event. And then when I submit my computation, I can say, so there I capture anything by reference, and I can say after my submit and before my parallel for, I must say my CGH, which mean actually command group handler. I can say there, it depends, the current action, it depends on U1, meaning that this computation will not be done before U1 is finished. And then I'm doing another computation, the copy back, and just the same, the submission of my square computation return me E2, and I put it in a depend zone on the copy back of the data. But as I said, I still need this final queue wait before I can look on the host, I can look on the results. There, if I want, I should have put event E3 equal queue submit and then say E3 point wait. Should have be more consistent with the rest of the example, but that's the idea. Just remember, anytime you submit something on the queue, you get back an event that can be used as a prerequisite for other actions. That's also, I think, if you want to do something with several queues, using several devices, you should be able to use this to synchronize between the different queues, what you cannot do with any other way. So that's for the events. So the practice. Oh, moving on. So as usual, better if you are at ease with the concept of the C++ Lambda, we put them everywhere. So you should have a clone of this Grayscott Sycl setup repository. If you are using Docker today, we will use those images, ICPX CUDA for the Intel implementation, ACPP CUDA for the adaptive CPP1. So you'll need to Docker pool them. You'll find in the slide, which are in the repository, the usual links to the reference guide, etc. This is the machine like last week where I'm doing my timing to check what is going fast or not. So today we will use this RTX A-simil for the test. For the numbers I'm giving, you will use your own on your own machine or servers. And so to get the training material, you should clone this Grayscott Sycl setup. Nearby this one, Grayscott Sycl GPU, and that's okay. Put the addresses also on the Discord. And so let's start. Okay, try to make it big enough. So that's the README of the Grayscale Sycl GPU repository. So just giving the usual information. You should have also the setup if you use the CMake from it. We will use, as compared to the complete Grayscale bench application, we'll use a simplified use case, just doing 50 images with 10 steps between 2 images to go faster for the demonstration. So new this year, you can use either Intel implementation or adaptive CPP1. Normally, I made some improvement as compared to last week. If you just run those kind of Kokkos bash, it may be able to detect, oh, it's ACPP or oh, it's ACPX. If it does not, you can explicitly say Kokkos ICPX CUDA or Kokkos ACPP. First difference between the two implementations. When using Intel, as far as I know, but you can complete me on Discord if I'm wrong. As far as I know, when compiling with Intel, you must say in the targets, the Sycl targets, I want to prepare a binary for CUDA, or I want to prepare a binary for CPU, etc., for the kernels, I mean. With adaptive CPP, at least the recent releases, you don't need to. He will discover on the fly. He has some default setups and will discover on the fly that, oh, I need something for CUDA, I make it. So that's why I don't need to say, to have a specific CMake for CUDA with adaptive CPP, at least as it is installed on my machine. He will just discover on the fly. So for the automatic way to run on different machines, I found that ACPP was a little better on this point. So in the repository, you have different directories, device, demonstrating selection device, etc. We will see more after. And the practice are the directories named step 0 to step 5. Not sure if the 5 is the right number today. No, it's not up to date. The step 2 has disappeared, so forget about this. So let's start with the warm-up. So warm-up will start from a CPU code and move it to GPU, I think. So you can directly work in your copy or make your own MyGPU project. Have a look at the script, which is doing the CMake execution, make execution, runtime with the arguments, etc., to see how it works. Or you can directly run it and see the demonstration. So the first step is just try to set up your environment, run it, and check what are the runtimes you got. I think I'm not sure what is the initial code. Let's check together. Where is my working work there? I will make it bigger. So let's inspect a little the starting code. So I'm in the Git repository named Grayscale Sycl GPU. There I will move to, we move to the step 0 directory, then give a look at SRC, and the starting code is Grayscale CPP. Also, I made a small difference as compared as last week. The code which is never changing, I move it to this Grayscale header file, just to review it quickly. So what I have in my standard header file, I'm saying that real for the practice is float. If you like, you may try to change using real for double just to see how it works and what's the performance. With these two constants, real 0 and 1, which I'm using there and there, the usual numbers for our Grayscale simulation, the usual pattern. You may want to use a different pattern if you like. There are better ones. That's the one we agreed on in the school. I have this code which is detecting and displaying, am I running on the output, am I running with adaptive CPP or with Intel? This drop function is the one which is taking the array representing either U or V in my reaction and putting a kind of drop of U in the V or V in the U in the middle. This function insert is taking my original image with the right size and duplicating it in an image which is just a little bigger with a border of 0 outside. Okay. Extract is doing the reverse, taking my image with the additional border which has been computed, simulated, and taking the central part to put it back in my original output. Analyze, which is doing a kind of fake, very fake analysis, just doing some kind of mean value of my image, just to check I've not broken anything. So that's the other file, which will be the same all along the practice, so you don't care so much. Let's now review the original code, which I see is written with buffers. So where's the main? Here's the main. So I'm printing the compiler I'm using just to check I'm not mixing Intel and adaptive CPP. I'm taking on the command line number of columns I want, number of rows, number of image, iteration, etc. I'm checking it's multiple of those values because I will use them perhaps or not to try the ND range. I check the number of iteration is a pair, because it will ease my code to be sure that when I'm doing my double buffering between the U1 images, the U2, that I will iterate an even number of things so that the final value is in the U1. Just to be sure, I'm using an even number so that I don't have to check every time if is the final value in U1 or U2, which is not the aim of this practice. There I'm recalling the arguments and then doing the actual job. So for the moment, I'm doing my queue with a CPU selector. So my starting code will work on CPU. I'm checking, getting the device information and displaying on the output, again, to check where am I running. So there, I'm preparing two initial arrays of U and V. So with the size which has been asked by the user, I fill them, the U with 1 everywhere, the V with 0 everywhere. In my U, which has 0, 1 everywhere, I'm dropping some 0 in the center with this drop. In the V, on the contrary, I'm doing some V in the center with the 1s instead of the 0, okay? So my initial U is just 1 everywhere except at the middle where I have no U, and V is the contrary. And then I'm starting the process, and when finished, deleting U and V. So what is doing process images? Is initiating my result, which is a mean on all the images, just to be sure I have always the same result, okay? Then I'm doing my extended images. I'm adding a border of 0 for my stencil to work. So the size are the original ones plus 2. I'm doing those 4 arrays, U1, V1, U2, V2, so that I will, at each step, either take U1 as the input, compute the result in U2. Next step, taking U2 as the input, putting the result in U1, and again. So there I'm putting 0 everywhere. And as a first step there, I'm inserting, so I take the content of UH, meaning U on the host, in U1, which will be used in the device at the moment. I am there duplicating my original V host on V1 to start the process. So I have my collection of arrays on the host. UH, VH, U1, V1, U2, V2. For all of for those ones which will be sent to the device, I'm doing buffers on top of U1, V1, U2, V2. And then starting to produce my images. So I'm doing NB images. Each time I will call iterate, which will do NB iterations. After each set of iteration, I will use these host accessors to take the values of VB1. So I'm doing V host accessors on VB1. I extract the corresponding pointer to call extract and to copy it in VH. So taking the buffer, where is the result? Put it, which is in an extended image, extracting the result to put it in VH, which has the original size, then computing my pseudo analysis, a small dot, etc. So what is doing iterate? So iterate receive the queue, the 4 buffers. Each time I will take the first one and copy in the second one and swap. So I prefer to call, instead of U1, U2, I prefer to call them input U buffers, input V buffers, etc. I have the size, which is the extended size. So I will do NB iteration, and each time I'm submitting a job to the queue. So I submit, I do the accessors on the buffers, and then for the moment, not doing, just mimicking what happens on a sequential code on CPU. I'm not doing a parallel for, I'm just doing a call to a single task. If you remember last week, we have seen that if there I'm putting a parallel for, Sycl will try to do multi-threading. And we have seen that multi-threading on this process, on this use case, etc., is not efficient, does not pay for. We'll go faster, but using many cores and wasting many resources. So I'm starting from the point which were the better one with CPU, just doing a single task. And so the single task will, there I have the stencil. I'm doing 2 loops on row and columns. For each of them, I'm applying my pattern, computing the Gray-Scott formula, storing the result in my output accessors, and that's all. And once my submitting of a single task is finished, I'm swapping the buffers, which will just, it will not copy data, actually. It will just swap, as for a vector, it will swap the internals so that my U1 becomes U2, etc., and again, and again, and again, and again. So remember there we are using a single task because we don't want, we are on CPU for the moment, and we don't want to waste time with multi-threading, which is not interesting in this use case of now. So back, after the comment of the starting code, back to the practice. So try to run this, look at the numbers. You've seen I've run it on Cassidy. I'm not sure why, but I noticed that in my last test, Intel was running a lot slower than adaptive CPP. So the usual guess is one of them is vectorizing and the other not. But I'm not sure I can explain why, but that's not the focus of the practice, so not a problem. Perhaps you will see different things on your machine. And so the practice is to run, the first step is run on CPU, on GPU. So what you have to do, you replace the CPU selector with a GPU selector. Then you should notice, oh my God, it is very slow because we use a single task. So if my single task is running on a single thread item of the GPU, you can guess why it is so slow. So after the next steps is to replace the single task with a parallel for. And the third question, I will not give you the answer now, is why it is crashing at the end of the job of the work. So try to figure out why it is crashing and solve the issue. And if you are in a hurry, you may look not too fast, I hope, but you have the Grace Code Soul as a solution. So let's try this for 5 or 10 minutes. I will, in the Discord channel, I will put my usual poll. Have you succeeded or not? To be sure, at least one of you has finished the exercise before we go on. So please, if you do this, understand, find the crash, solve the issue, go to the poll to say I'm okay, so that we can see that some of you are progressing. So I'll let you try. We'll start the poll. There is a question on this. In which channel? Question experts. Does the events need to be passed by reference? I don't think so. To be checked. I would, when writing all the examples, the application, etc., I never mind about is it by value or reference. So I guess that's okay. It's kind of improved pointers probably. We'll see at the end, but I think in the final example, we're even doing vectors of events, so I think they can be duplicated as much as we need. I have two people which succeeded, so I'll let you still 4 minutes before we discuss what comes after. I see that Matisse is able to run on the integrated graphics. I discovered last year, we were seeing on my machine, at least I was seeing the integrated GPU in my machine, not the discrete GPU, I was seeing it, but not this year. And I was said by Intel people that now if you want to see the integrated GPU, you need to install some dedicated drivers. They are not anymore installed by default with one API. So I've not tried, but you should do dedicated specific things if you want to see the integrated GPU. Using the integrated GPU is fun, but if it's on your own machine, you will freeze your machine. So don't get trapped in this. You start a very heavy things with your integrated GPU, and anything is frozen, of course, because the GPU is done for your display, not for computing. But it's funny to try. Something I can say also now about integrated GPU for the test is that most of what we will try after is malloc shared, malloc device, and improve the I/O between the GPU and the CPU. And of course, if you are using an integrated GPU, it does not make sense because they're not such thing as copy. The integrated GPU is sharing the memory with your CPU, so there's no transfer. And you will not see the difference between the different I/O strategies. So replace the CPU selector with the GP1, straightforward. So that's slow because single task running on just one computing item of your GPU, of course, not optimal. So you put the parallel 4 using the full GPU, and it should be okay. Let's see the crash, the reason for the crash. Quite easy too. What's the problem? Let me check in process image. You see there, I'm creating my U1, V1, U2, V2 with my command new, prepare them, do the buffers, and finally deleting my U2, V1, etc. as expected. I've done the new, I'm doing the delete. The problem is that I delete them first, and the buffers, they will be deleted after when I'm at the closing curly brace. They have been created there with usual object on the stack, and they are destructed when I'm closing the curly brace of the function. So I destroy the buffers after I destroy the arrays which are underlying, which are under the buffers. That's why I have a crash. Normally, until the buffers is destroyed, you should not touch the underlying arrays. So if you destroy them, of course, when you arrive to the destructor of the buffers, it will crash. So you must change something. So I'm not sure what I did, but in the solution there, yeah, I moved the creation and destruction of U1, V1, U2, V2 from process image to the main function. And I just left the process image to make the buffers. So to be sure that the buffers are destroyed first. But just remember, you use buffers, you should not touch the arrays, not read them, write them, nor destroy, delete them before the buffers have disappeared. For what concerns the timing and the performance, so also one point which may be important, especially with Sycl. Remember, Sycl has in mind, I run anywhere, I discover on the fly what's on the device, and sometimes I discover a new hardware and I recompute my kernel on the fly to adapt to the GPU I'm founding where I'm running, okay? So there's on-the-fly compilation, final compilation. Sometimes I think that with Intel, etc., for GPU, NVIDIA, the kernel is first compiled in some SPIR-V intermediary representation. And when arriving on the final real GPU, transform this in the final binary on the fly. So the first time you run a program in a given place, you will have those additional time taken to finish the compilation, to complete it. So if you want to do some timing to have a guess of what is going on, you must run your program at least twice, because the first run will finalize the compilation, okay? That's why if you want to have a look and see if it's performing well, you run it at least twice. In my test, I run them 6 times generally. I throw away the first one, which is finalizing the compilation, and doing some kind of taking the median value for the 5 other ones. And so in Cassidy, I got this. So you see, also, as I said there, that's a practice. That's not a benchmark. Don't take the numbers and think, oh, okay, Intel is going faster, adaptive CPP is going faster. The numbers, if you run several times, you will see that the numbers vary a lot, depending on, even on this machine, which is doing just that in a server, not doing anything else. I run several times, I see that I have perhaps 20% of variation on the performance. So please, that's not a benchmark. That's just a way to have a first touch on the performance. And we see we have something similar, actually, between the two implementations of Sycl there. And so it was taking between 2 and 10 seconds when running sequentially in the CPU. So now, of course, we are going a lot faster. At the moment I made this diagram, I'm not absolutely sure it's the most recent one, and the numbers may be different today. As we see there, I made it 2 years ago. But just to show you what's happening with Insight, we are looking what's happening in the GPU. So that's the end there. The blue is the end of the set of iteration. And when finishing the iteration, we see those red and green blocks, which are the transfers of data, which are done by the buffers accessors. You have seen my solution. I don't say I don't put any copy in it. the runtime is doing it for me, and that's the place where I'm doing some transfer of data. Is there something else to say? So yeah, I noticed there was something strange. It's normally when you have finished iteration, you just want to take back the result. And if you look at inside, you see that it is sending back things afterwards. I have no idea what, because normally we just need to download the result and let the GPU goes on the next iterations. But as we see with Insight, apparently after the host accessors get the last images, he's sending back things. What things? I don't know. So let's see the step one, the next step, which is to play a little with the list and the selection of device. Because again, we are in the spirit of Sycl there. We are running somewhere. We don't know what are the devices. So let's have a look. Remember the Sycl ls, it's a bonus command of Intel, which lists you the device, but you don't have it with adaptive CPP. It's not in the Sycl specification, but you can write, do your own quite easily. So first steps is move to the device list repository, have a look at the code, play with it. Move to device select, have a look at the code, play with it. We'll do it together also. And the practice is that you try to change your project, your code, the one we used in step 0, so that we can either choose to run on CPU or on GPU with an argument on the command line. So actually make your own selector, looking at argc, argv, and saying, okay, I will run on GPU or I will run on CPU. Let's have a look at those example device list and select. So what do I have in device list? So in device list, I made this this function, which is taking a device as input and displaying many information, which are the platform name, which means more or less what we usually call the backend. Yeah, perhaps it is worth to remind that actually Sycl does not work alone. Generally, there's some kind of backends to address the different kind of device. For example, on CPU, in the implementation of Intel use an OpenCL backend. The one of adaptive CPP use an OpenMP backend. So you will not see the same platform information. All of these depend on the installation, actually. So we have the platform name, the name of the device, the name of the vendor. And just to check, you can look on the device. If you can ask it, are you a CPU? Are you a GPU? Are you an accelerator? In this context, you should understand accelerator as a FPGA, actually. Because Sycl was designed with FPGA in mind also. There I'm testing if I'm doing default selector on this device, what is the number which is returned with CPU, GPU, etc. What are doing the selectors? Actually, they are expected to return a number, which is kind of a rank or evaluation of the power of the device. So you can make a selector yourself, which is very simple, just saying 0 or 1 or something like that. But normally, you give a number so that if there is several devices on your machine, Sycl will use the one which returns the bigger number. So we can ask there the CPU, GPU, accelerator numbers. I have this print function, which is just doing the name, printing the name of the device. Try selector, just a templating function to try several kinds of selectors. That would be a way you can use to loop. That's what is done by Sycl ls. kind of loop. You can loop on all the platform you call Sycl platform, get platform will return you a collection of all the available platforms. For this platform, you can ask, give me the list of all devices. So you can loop on all of them. There I'm just printing what I call the rank, the first one return, the second one, etc., and calling inspect to check the information. I remember also that there's no rule about the order of the platforms and the order of the devices. So if on my machine, my GPU is the device of rank 1, on another machine, on yours, it may be different. So you, in general, you do not use the rank in the list, the rank to select your device. You will rather say CPU selector, GPU, or the one which has NVIDIA in the names, those sort of things. There I'm trying different selectors. I can even try to run it. Let's be to run it on Cassidy. Do I have the network working? Yeah. Okay. Don't worry, those are secret scripts I use to start my Docker. I will use, for example, the Intel one. I will use the image ICPX CUDA. If you're using Docker, don't forget when you start your Docker image, you have some kind of secret commands, -GPU all or those sort of things, or you will not see in Docker container, you will not see your GPU. So if I try, we are doing device list. So my, my script does not guess I'm using ICPX. It should. Okay. I will. Perhaps I'm not up to date there. Let's say. Okay. So there I'm doing. That's the CMake. Then the call to make the build. And then what do we have there as output? So when looping on the platform, then looping on the device, the first one I have is my NVIDIA card. The platform name is NVIDIA CUDA backend. I guess it's the name chosen by CodePlay, which has done the NVIDIA plugin for Intel. The name of the device, vendor. If I ask, are you CPU? Obviously, he say no. GPU, yes. And you see that the default rating, the number returned by the default selector is 500. If I ask him, what is your rating as a CPU, he say -1. That's a way to say for a selector, I'm not a CPU. And as a GPU, his rank is 1000. And then I have my CPU, which is behind an OpenCL backend with different numbers. If there is a check that if I say nothing when doing my queue, I will have the NVIDIA card. If I use the default, I have the same. If I ask for a CPU selector, it is selecting this device, which is the CPU, and with a GPU selector, the NVIDIA card. Okay. That's all consistent. If I look at the device select, I think I have done something which is not that good, but that's just for the demonstration. I've done something based on the rank, I think, yes. There I'm saying on my command line, I want the device rank 0 or 1, and that's my on-the-fly selector. I just capture by a reference this rank, make it greater each time for each new device, and once my current rank is the same asked by the user on the command line, I return equal, so I return 1, and for the other one, I return 0. So that's an easy way to say, I want the device 0, I want the device 1, etc., which we do not do in real life because the rank, they can change from one machine to another. So that's just for the demonstration. So please, on your side, try to do your lambda there in your code, a lambda which will select CPU or GPU depending in the user on the command line has asked for CPU or GPU. You may think it's more a C++ exercise than a Sycl one. But I insist on this because we are really in the spirit of Sycl that we are preparing a code and we may run it somewhere we don't know. We will discover on the fly what is the device available, etc. On the contrary of other system where you, at the compilation, you fix anything and it's ready to work on a given material hardware. That's not the spirit of Sycl. The spirit of Sycl is whether I run it where I can and I discover what happens. Oof, when done. Remember, you have the queue. When you are creating the queue, you should give it a lambda. This lambda we will call on all the devices available where you are running. And your lambda function should take this device and return a number for each of them. And the system will keep the one which has the greater number. There's many ways to do it. And we wait until 10. Okay. So let's comment on one solution, but there may be many. So actually, I think I reused the existing selectors, tricky writer. So there I'm having a new argument, which which is the first one, which I call device type. I put it in a string. And then when I create the queue, I'm comparing, is this string CPU? If this string CPU, I'm building, yeah. Actually, let me look. I'm not using a selector in the solution because you can first choose your device, then do the queue, or you can use a selector as I've shown before. There, I'm doing what? If the device asked is CPU by the user, then I'm creating a device with the selector, which can also be used actually to create a device, not the queue. I can use the same selector for the device creation. If the argument was GPU, I'm creating a device selected with the GPU selector. And then when I'm creating my queue, I give it device as argument. That's a way, among others. I could use a selector, as I said before, or as I have shown in the slides. You have another way to do it. One thing which is quite easy to do with this kind of mechanisms is that you may want to say, okay, I'm using the default selector, which is selecting the best device on my machine. And after that, I look if is my device a CPU. If it's a CPU, I may start a task which is submitted as a single task, because I know that it will, for my problem, it will be better with a single task on CPU. And if my device is a GPU, I will start the one which is using the parallel for, so that my program, whatever happens, wherever I run it, if there's a GPU, I will do a parallel for. If it's a CPU, I will use a single task. And with Sycl, it's quite easy to do. You can do it without Sycl also, of course, but you have all the material, all the code to do it quite easily there. So back to the practice. So we've seen how to select the GPU. Actually, I think it's better to make the break now. I will break. Can I change the time or not? Yeah? Karim, can I stop now and do the break until 11:15? Because people who want to follow remotely GPU for Sycl, they are already there, so they know about. So it's better to stop there and to do the final things about I/O afterwards. So I suggest now a break until 11:15, if everybody is okay. So go. So 30 minutes break and back at a quarter to 11. C'est bon? Okay, so welcome back. So in this second part of the practice, we will focus on a key point when you want to run your code on GPU, which is transferring in general, if you want to use an efficient GPU, it's what we call, let me remember, a discrete GPU, meaning it is not integrated with today, not integrated with the GPU, and it is a GPU which has its own memory. And so one of the challenges when you want to use those discrete GPU is to move your input data to the GPU, make the computing, and then move the data back on the host. And it's why also for some problems, it is not worth. If you are not computing enough things, the time that you lose when moving the data to the GPU is greater than the time you save computing there. So you need to try to find a good balance and to check that your use case is worth to be used on this kind of GPU, because you lose time moving the data, okay? So we'll see now different ways to handle this move of data. And so the first step that we will investigate now is to use the shared malloc. So that's in the original Sycl, Sycl 1.things, you just have the buffers on accessors. And starting with Sycl 2020, we have this new unified shared memory, some new ways to allocate data and move the data. And the easiest one, which is called lazy because it's easy, but not the most efficient, as we will see probably, is the shared malloc. And then the idea there is that instead of doing a usual new, as I showed you in the slides at the beginning, instead of doing new, you will do malloc shared, which return you something which look like a usual pointer, but which is usable both when running some code on the host or when running some kernel code on the device. And it's the underlying system that will detect when you follow your pointers to get to the data, that will detect if the data is there or not on the GPU or on the host, and will move it automatically to make it available. And so you do not need to care. It's why we called of unified shared memory. It's just like there was a single memory and the system on the way is doing the move for you. So the idea of the step 2 is that you can have a look at those square buffers and square shared examples, and you use it to transform the starting code, which is in step 2, donc step 2, SRC, Grayscode, CPP. You take it as a starting point, or your own code if you have make your own project, and to replace the data allocation with malloc shared. A point there is that once you do that, you will need to put call to wait in the right places. Because before, with the buffers and accessors, the runtime system is doing it for you, waiting at the right moment. But once you are using malloc shared, it does not do the job. It does not know when you want to read, when you want to write. So it's your job to wait at the right moment. And remember, every time you submit a task to a queue, you get back the end immediately. It's asynchronous. The job will start on the device, but you do not know when you do not wait for it to be finished. You get the end back immediately. So when you need to be sure that this task has been finished, you must call wait. So that's the exercise now. Replace a malloc free or new delete in your code with Sycl malloc shared and Sycl malloc free to give the memory back. Remove the buffers and accessors, etc. And if needed, if you think it's needed, add wait. And check that your final number analyzed has not changed or you have broken something. A few clues that are worth mentioning is that one nice thing with the buffers and the accessors is that they handle for you the dimension too. But with the row pointers that we use with malloc shared, we are back to the real C++ world where we do not yet have the 2D indexes. So you will have to compute yourself if you are in a single memory area and you want this row and this column, what element it is. Because these work which were done by the buffers and accessors before are not anymore done for you. So you have to compute, which is quite a typical exercise when you do this kind of code, but it's a pity that you need back to do it yourself. I guess at the moment we will have MD-span in C++ finally implemented somewhere, so that we will have multiple index available also. But in this exercise, I think we do not have a MD-span yet, so you have to compute your index yourself. And also, if you wish, since we do not have those buffers, stories with delayed crash, etc., I think it's better to move back U1 in the process image. It will be more clean. So please try. I'll let you 10 minutes to try this, and then we'll comment the solution. And we'll see, you will see on your machine, and we'll see on Cassidy how fast malloc shared is performing or not. While you're trying, I may try to comment a little about the example square buffers, square shared, if you wish. So the example with square buffered, so just doing an array of size 10, so a queue from a GPU selector. I'm filling my static array with the values, doing buffers on top of my input and output static arrays. And then I submit a task doing the accessors. And finally, the parallel for on the elements to square them. Then I print the result, and I access them with my host accessor. So with the host accessor, I'm sure that it will wait for the computations above to be finished, display the result, and that's all. So the same with square shared. The queue was before. Now, instead of doing static arrays, I'm calling malloc shared for the given size, filling the input size with my usual values. And then, because I do not need buffers, accessors, I can directly call queue parallel for where I'm giving the range I want to loop on, then the lambda, which is done directly using my pointers. But before printing the result, I need this Q wait, or the program will directly send the parallel forward and then print before it is computed. I do not forget to do a cycle free for each cycle malloc shared, and that's all. Very simple. So on your side, with Grayscott, the more problem you have will be to compute the 2D, the index, because you are moving to 2D. I have a question for Joël. I was thinking in this exercise, we compute the index. We compute the index by yourself quite easily. You take your column numbers plus the row numbers multiplied by the number of columns, etc. That's something we are doing very often. So I do it in the exercise, but I think in Sycl, I guess they have made a few functions for this. You know about?
You have get linear ID and stuff like that.
If you want to avoid to code it yourself, I think Sycl is providing a few utilities.
But you have to call it directly on the ID object or whatever.
Sorry?
You have to take an ID object explicitly,
Yeah.
and then you can call that.
Yeah, so you can avoid to compute it yourself. We do it so often that we don't care, but if you're not at ease with that, Sycl is providing a few utilities for this. I should use them in the solution, would be better. Yes, we have one yes. Okay, I'll let you 5 minutes more. One yes, not so much. If you have succeeded to make it, please tell us in the channel in Discord. Does it go faster or slower than buffers accessors on your machine? I'm not sure that there is a single universal answer.
For me, it's a bit slower.
A bit slower.
Yeah, but like 5%, 10% slower.
Yeah, so it's not a definitive result
no,
because
yeah.
depending so much on the runtime, but for me too, as we will see. For me too, on my benchmark machine, is a lighted machine. I can see the say, okay, we have 2 yes. So let's go forward a little. But we have time, so don't worry. You can go on trying. So a comment on the grayscotesol.cpp in step 2. So my main, as usual, print compiler, look at the arguments. Now I have the new one, this device type, so that you can runtime choose I want CPU or GPU. My construction of queue, depending on the command line arguments. For the arrays, which are the arrays with no border, that only stay on my host machine, I don't need to do malloc shared. I will do malloc shared only for the data which is moving from the device to the host, which are the images with the border, okay? So the usual one, I still goes on with new real as before, fill them, etc. Then I call my process images. So let's move there. So there I'm initializing my magic number, then preparing my U1, V1, U2, V2, which are the data that will move back and forth with the device and the host. So there I'm calling malloc shared of reroll. The number of elements is the extended number with the borders. You will notice that I need this Q argument when doing the malloc shared. So I'm saying this data will be exchanged with this Q, which is connected to this given device. And then I can fill with my real number and then insert. We take the values from my host arrays and put them on U1. So there with stdfill, which is a standard algorithm of C++, or insert, which is a function I have written before, they are waiting usual pointers. I give them usual pointers, and I use them as if it was the same memory between my CPU and my GPU. So there I'm writing there my initial values and call, start my loop on the images and call iterate. And iterate, I give them my U1, V1, etc. So let's have a look at iterate. So iterate before was receiving buffers. Now it's just receiving pointers and use them directly. There you see I'm using input U, input V, etc. as I would use any kind of pointers. There's nothing special. There's no buffers, there's no accessors. And when I'm reading there the input U, the underlying system will see, okay, I need this data that was written before on the host. I will move it from the host to the device to make it available on the device. All without any control needed from me, it's automatic. So my usual work, but then that is new. Before the swap, before swapping my pointers, I wait that the current iteration is finished. If I don't wait, I will swap the pointers. At the same time, the device is working on the memory, the system on the line will get mad. So this wait there is very important. And because I have this wait also, I know that in my process image loop there, I know that when iterate is finished, the computing is finished, and I can extract and I can analyze, no problem. So back to the slide, or I could try to run it live. Quite funny. So I'm in step 1. No, I'm in step 2 now. Step 2. So this command, this script is running the initial code, so with the buffers accessors. So as I said before, I run it 6 times actually to be sure that the on-the-fly compilation is finished and to look for the mean value. And if I want to run the solution, if you use the same script as me, you have to give it more information. You must say, I want to run, I'm using the CMake ICPX CUDA. I want to run Grayscott Sol, and I want it on GPU. And this one will run the solution. And normally we can see that the first one is longer. You see that there, the first one is 1 second and 60 milliseconds, and the following one are rather close to 900 milliseconds. So we see the effect of compilation of the fly. So that back to the instructions. So we'll remove all buffers and accessors, add the needed weight, make some malloc shards. I did not comment on the computing of the index. Let's go back there. You will see there that I think it's in iterate. Yeah, there you see I'm computing my 1D index from the current column and the row. Because I've made a malloc shard, so I have a 1D area of memory. So I must compute myself for this row and column, what is the rank in the 1D memory. So there I have this kind of computing. I did before already for the pattern, but I must do the same for my, my index, which is used when I ask for EU or EV. For example, there, the more simpler one, this one, you see, I know that the UV I want to read, it's the current row R plus 1 and the current column C plus 1. So in 1D, I get it using a row plus 1 multiplied by my number of columns plus the current column rank. That's the way to compute it. But as I said, you have utility function in Sycl if you need to do this computation for you. That's the 1D, 2D translation. So back there. So the times I have using ICPX, Intel, or adaptive CPP, quite close as usual, but quite longer than before. And actually what's happening is that it's all automatic. And if you remember the inside view we had before, that was that with the buffers accessors, iteration finished, download result, upload something, then start new iteration, okay? So what we have now with malloc shared, it's a mess because each time I'm accessing this or these values, the system behind say, oh, there I need this value, transfer it, but that's not transfer all the image, just a piece of it. And then at the next steps in my loops, it needs the following data. Oh, I miss this data, take a new small part of it, get it back. So all this mess in the input-output, which we don't see because it's automatic, not completely a surprise that it's less efficient than when we transfer the whole image one way or the other. So the next step, as I said before in slides, etc., is that, okay, malloc shared, it's easy. If it's enough for you, if your problem, you don't need more performance, it's the easier way to work. It's even better to do buffers on accessors because it's very meaningful. You see who read, who write. So we are often asked, if I want to write a Sycl code, which should I use between all those ways? The usual answer is you start from nothing, from scratch. Better use buffers accessors because it's the clean way, in one way. You are giving the more information possible to the system. So we would say it's the best. If you're starting from an existing code, the easiest path in general is to move to malloc shared. And if the performance is enough, just stop there. If not, if you want to get more performance from your hardware, then next step would be to move to malloc device, where you control what you create as an area of memory, where, and when you explicit the copy. Because the problem there is that you don't need to explicit the copy, but the automatic way is not so good as it could be. So you know in your problem when you need to copy what, so take the control. And that's what we do with device malloc. So now we will have a look to square device, which is the way to do it with malloc device. And the exercise to try on your side, on your code, is to replace malloc shared with malloc device. That's the easy part. But after that, you will have to add copy commands. Or your computation will be on bad input data. Let's have a look at the square example. Which is square device, SRC. Oh, it's empty, my God. I've lost my file. Oh, I will look if I find it locally. Don't know why it has disappeared. Very strange. Let's try there. But I have pushed everything, so I will probably have to search it in the history of my Git repository. We are looking in square device. We have even lost SRC in square device. Okay, let's try to go back. No. Incredible. One year back in time, my God. So here's the code. So as usual, it's in the old style. So queue with GPU selector, etc. I initialize my local array in the host with the input values. Then I'm doing some malloc device. So those pointers, I put a D in the name just to say it's a device pointer. I should not use them locally. It will not work. On the host, they make no sense. They are address which will be only usable in the kernel, in something running on the device. Then there I'm doing the mem copy. If you look at the reference, we will have a look. There's a way to copy with better syntax. But there, what I'm doing, it's a mem copy with the same kind of argument in the same order than the C functions. So the first argument is the destination copy of the copy, which is my device pointer. The second argument is the source of my copy. So I'm asking, I'm taking my std array, I'm calling .data to get the row pointers. Then the size I want to transfer. With this C flavor, I must compute the size in bytes. So I'm taking the size multiplied by the size of a float. And then I'm wait, because if I don't wait and start my parallel for immediately, the copy is not finished, okay? So I must wait for the copy to be finished, then calling the parallel for, when I can use my device pointers. Then I wait, and then I copy back the result locally So from the output to my output data, local data in the host. And wait again. A way to avoid all those waits, some of them actually would be to make a queue which would be there with the argument to say I want an in-order queue. This would avoid me this wait and this one. But at the moment, I should wait whatsoever, because even if my queue is in order, if I ask copy, compute, copy, I have immediately the end back, and I will do the output before the queue has finished its work. So again, even if I make it in order, the in order applies to what is inside the queue, not my host code. So if I make it in order, I can suppress wait there, I keep this one, or after that, I put a queue.wait before I'm starting to print my result, okay? So try to do that in your code with the Grayscale simulation. And perhaps, in the meantime, we can try to find in the reference the alternative to this mem copy I dislike. So let's try to find this. That's the documentation. I'm sorry. For Sycl, we have this reference documentation that you can find in my slides. You have the link. You can find it in the Chronos side. And there, if I try to find a mem copy, where is it? This one. So you see, you have this mem copy, which is a C style, and better, you have this copy function, which is the C++ tag, where you first give the source, the destination, and the number of objects. So prefer this one, of course. And also, if you want to put some data directly on your device, you may call this memsem, which is a C style, or this fill, which is C++ style, doing the same, filling a device array with some numbers. If you have questions, you remotely you can take the microphone or ask in the discourse channel Sycl course or in the room. I can help. Tom, you're not the first one on my log device.
Sorry, I have a question.
Yeah.
Why the main contribution to the running time is still due to the user?
The
well-
user time?
Well, I mean, why the user time and the sys time is so close with Sycl always? Because I would have expected that one of them
I'm
will
not
be very
sure.
short and the other one will be.
Yeah, I'm not sure. I have asked it to the experts, the Muppet Show at the last rank. I think they are not sure themselves, from what I
Okay.
feel. How the time which is, especially how the time which is spent on the GPU, is it taken into account in the user time, the sys time, the real time? The real time for sure, we have it. But between user time and sys time, I'm not sure. But Andrea, perhaps Adrien
This
can answer that.
depends on the implementation of the GPU driver. In principle, in an ideal world, which is not the world of GPU applications at all, you would like the GPU driver to stop taking CPU time while GPU work is executing. You just stop doing CPU work and do something else, and this would then not be accounted as either user time or CPU time because you're just sleeping. In the real world, experience shows that GPU drivers can use enormous amount of CPU time in either user mode or kernel mode for, in my opinion, no good reason. But because this is often proprietary software, it's hard to profile it and figure out why it's using so much CPU time. So your guess is as good as mine.
Thank you.
And even on the CPU, perhaps you noticed at the beginning of this practice or last week, but when using adaptive CPP, everything seems normal. But when using the Intel implementation with a single task, we should use mostly one core doing the single task, and we see some kind of huge system, which is quite hard to explain. And especially we see a user time which is greater than the real time. So apparently, for some reason, the Intel implementation, even on CPU, will use several cores. And so one of the things perhaps we'll try this summer to investigate, but quite strange, but okay. Especially with the Intel implementation, apparently sometimes we can easily use several cores to optimize things that we do not master. Okay, so let's discuss the solution for the malloc device. Where am I? So we are in step 2, solution. Okay. Step 2, step 3. No, we are step 3 now. Yeah, I think we are step 3. So I will start from the main. So my main, how is it as usual beginning. Oh, yes, for some reason, at this moment, instead of new, I use vectors. We don't care, that's the same, it's better, it's simpler. But it's good for data which stay on the host whatsoever. So I can use a vector. It's better than using the new as before. I call my process images. Then I'm creating here my usual U1, V1, U2, V2 with malloc device. I add this D to the name to remember it's only okay on the device, to be sure I don't try to use them on my host. Perhaps that was the difficult point, is that because I do not buffers, I need to make a new local image in my host with the border to prepare my work. Starting from my image with no border, I put it in a local image with the border. That is the one that I will copy afterwards on the device. So there I'm having this new UH like uhost extended image and vhost extended image. I'm taking the original ones and put them there with the additional border of zeros. Then preparing my device, my malloc on the device, and then doing all the first copies. I'm copying my uhost, vhost ext on u1d, etc. So starting to copy anything on the device, then wait for it to be finished. I need .data there because I've done some vectors locally. Forget this for the moment. I should have removed them, but they're still there. The process, so I call iterate, and then I made 2 functions, iterate, which is doing the iteration on the device, and download, which is the action of taking the result back to my host. So I'm doing iterate, n times, download, extract, etc. for the number of images I want. So let's have a look at the 3. Those 3s correspond to the malloc device. Let's have a look at iterate. So iterate, receive my device pointers. Work as usual, I think. just as before. For him, he was having malloc shared pointers. Now it is having malloc device pointers. From the point of view of the kernel, it's just the same. I have this new function download, which is doing the copy back. So from there, for one time, I'm using copy, not main copy. So I'm taking from, which there will be called with V1D. This one is the pointer to the V1 device. I want to copy the result to this vector, which is the local VHX vector with the size. Then I wait to be sure it's finished. There I wait also explicitly. And so you see there in my main loop, I'm calling iterate, working on the device, then wait, then calling download, taking the result locally, and doing my usual extract analyze. And that's all. So if I look at the performance, so the clues, you will need to do more extended image on the side, one more. So no need to copy back. Your data is on the device, can stay on it and be used all along the simulation. And what we have in the performance, you see a quite great improvement. Why? But simply, if you look at the insight, what happens, I have scaled, use a greater scale, but basically, when my iterations are finished, I download my image, and that's all. After that, I start my new iteration. There's not these strange things we noticed with the buffers accessors. I don't know why the buffers accessors, they were moving something back to the device, but we know we don't need to. So there we are doing just one copy, the only one we need. And as you see, the performance is, of course, better. So the final big step, which is that normally the hardware, the GPU hardware, is able to, at the same time, compute things and doing I/O with the CPU. The hardware is able to do that. So how to express our problem and our code to get this ideal world where we are overlapping the I/O with the computation? Because there you see, during the download of the data, my computation on the device are stopped. But these new iteration there, they should be done at the same time we are doing the download. There's no reason to wait, actually. So we can fill this gap with computation if we are smart enough in the way we express the problem. So that's the last step, not the easier one. Is try to make some overlapping between I/O and computation. I will first command the starting point because I made part of the work for you because other way it would be too long. So if you look at step 4, starting code, I have already done one thing which is important, is to use the event. Because so to better organize your work, you will need to rely on events. So the starting code, it's the same as before, but with event explicitly. So for example, my call to iterate, it is receiving as input a list, a vector there. You see a vector of event, which I will declare as prerequisite to the computation. So when I call iterate, I can say to it, do not start before this and this and this event is finished. And iterate is also returning an event, which is the event corresponding to its own computation, saying the way for the external caller to know if it is finished or not, if the iteration is finished or not. So how it works, there I have my usual loop. And when I submit my first iteration, I said that depends on prerequisite, which are the ones I received when calling iterate. And when this part is done, after the swap, I will do a new prerequisite collection, which is the current iteration, actually, which will be the prerequisite on the next loop there. So I have this prerequisite vector, which actually contain, at the beginning, prerequisite contain what I received. And after the first iteration, it contained the last iteration I tried, so that each iteration wait the preceding one is finished. And when all my iterations are done, I'm returning the last one as the final event in the loop of iteration. Don't worry, it's written, it works this way. But you see, when you start an iteration of 10 steps, the first time you receive initial dependencies, then after you have started and finished the first iteration, this one begins become the dependency for the next one, etc. And this rolling this way. There I have my download as before, which is receiving as prerequisite actually is the last iteration finished and return itself its own event. And if we look at the process images, here we are. When I called iterate, there's work to be done after? No, not in this case. When I called iterate the first time, the input are an empty vector of events. It's the first one. There's nothing depending on. I've done my copies initial, but I have done an explicit wait. So there I started these ways. Then I call the download. As a prerequisite to the download, I put the event returned by iterate. So that download wait for iterate to be finished, okay? Then I wait explicitly on my download event before I do extract, analyze, etc. And again, I loop on it in the same way. So how to obtain some I/O overlap with the computation? I give you clues. So start from this implementation with the events. Then you will need a new V-array on the device. Why? Because there, if I start there my iteration, I may write on V1D, which is currently downloaded. So I may change the value of V while it is downloaded. So it's not good. So what I must add there is that when I have finished my 10 iteration, my last value of V, I must copy it in another buffer, which will be used by the download. And then I can go on with my next iteration on U1, on V1, U2, V2. So I need a V3, actually, to store my last results so that download can start on it. This time, while I'm downloading, iteration can go on U2, V1, U2, V2. But when they are finished, they will need to store the result in V3, but they must not store before the download is finished, because V3 is under downloading. So you have to set up those, you need to add V3 in the device. And then we have, for the moment, two actions. We have the iterate and we have the download. You must have something that you can call a store or shell or whatever, which is the action to take the current value of V1 and put it in V3. So you must mix these three actions, and you must set up the dependencies with the events so that the download and the next iteration can start together once the store is finished. One clue which is important, I've not found it in the specification of Sycl, but I noticed that when you start a download, a download event, it's blocking, at least in the Intel implementation. Download is blocking, is waiting actually. So you must absolutely, you cannot do, I start download, then I start iterate, because iterate will wait the download, because it is blocking. So you must do the other way. You must start next iteration before starting the download. So the order, if we are in the middle there, on top of that, there's complexities about how to start, how to finish. But if you are between two iterate, the order is iterate, finish. I start store in V3, and iterate must wait because until V1 is duplicated in V3, we must not iterate again. So I start store, all the other ones wait, and once the store is finished, I start to iterate again, then download. And this way, and that's the only way I succeeded to implement, perhaps there are other way, but this way, the iterate start and the download start together. Try it. But I warn you, it's not easy to make the good connection in the ordering to have the effect. Honestly, I will put a poll, but if someone in 10 minutes succeed to do this, he wins something. I can give it a book, my book about data parallel C++. But please try to see how tricky it is. Or that's something you can try to make afterwards on yourself. And please feel free to ask questions on the channel later on. Sure, I try to keep an eye on it. Gonzalo, make an effort. Try a little. I should not say that, actually. I should say it's easy, go on, go on. Oh, sure. Presenting the refreshing. I let you until 55 and we'll conclude. En fait, ça va pour faire des trucs ultra basiques. Ça va pas beaucoup dans les détails. En fait. J'aime beaucoup l'intro HPC, par contre. Je la trouve vachement par les auteurs. No yes yet. We don't go to lunch until there's at least one vote yes. Some people are hungry. So first clue, iterate has no change. I think it's just the same as before. I have this download, which has no change as before. And I have this new one called shelve, which is taking from and copying to real, I will call saying, please take V1B, D, copy it in V3. And the game, which I will not show you immediately, is to know which one should be called in which order, given which event. 2 minutes. Is someone trying in the room? Yeah? Okay. I let you your 2 minutes. Okay, finished. So one solution, perhaps there are others. So as I said, I'm adding this new malloc device v3D to store my intermediary results, copying anything as before. And actually, to get what I want, I needed to change a little what I'm doing in which order and to make a few things at the end. So what am I doing? First, I shelve what I've just copied. It's a waste of time, but it's a way to start the loop. Then I say iterate with shelves, a shelf event as a prerequisite, and download with a shelf as a prerequisite. As I said, at the moment when you are copying in the device V1 on V3, you cannot do anything else. You cannot iterate because you must not touch V1, and you cannot download because V3 is not ready. So first the shelf, then iterate, then download, because as I said also, when you download, it's blocking, so you must start the iterate before. So the ideal ordering in this problem is to shelve, then iterate and download in parallel, waiting the shelf to be ready. I'm also explicitly waiting after the download, even if it's blocking. It's better this way to be sure I can start the extract on the vHost side. So iterate start, download start. On the side on the host, when download is finished, extract and analyze are done. And I'm back there. And I start again the loop with a new shelf, but the new shelf must wait for the iterate, must be finished, to be finished. And once the new shelf is finished, again, iterate, download, etc. In this ordering, I cannot overlap. But once I'm outside, the last iterate, when I download and extract, analyze, the last iterate was not finished. So to get the good result at the end, I need a few more work on the last iteration after my loop is finished. I must download the last one and extract and analyze, or I will lack the final iterations. And that's all. So let's have a look at the result I got on Cassidy. And so I got these times, so it should be a little better as before. You see, I break the wall of 600 milliseconds. What was the previous time? Yes, you see, I gained about 100 milliseconds, grossly. And the case is that instead of this, I have this. So that's the end of a given iteration. This blue one there, I think, is the shelf, is the duplication, which is on the way on the GPU. And then I start iterate, download. And instead of this about 5 milliseconds, it was in 2 years ago, but it should be similar today, perhaps. But 2 years ago, instead of this gap of all the time in red, I just have this gap between two sets of iteration, which is the the duplication of V1 on V3. So of course, I've chosen to run my program with 50 images, 10 steps to increase the effect of I/O, etc. All of this highly depend on your program, on your use case. So there are use cases where it is very important to get this I/O overlapping, and other use cases where you don't care. So only do this kind of game if it is important in your use case, because it must save. It's a big effort to code, so it must be worth for what you gain in your performance.
If you don't make a lot of copies from the GPU to the CPU, you don't need to overlap.
Yeah. It's important if you are I/O bound, and you need to not to wait I/O all the time.
Yes, yes.
And perhaps I've not tried, but there I'm not doing the HDF5 files. Perhaps it would be important there also, because on the CPU side, it takes time to write the files. We perhaps may have even better benefits with this technique there to be tried. Okay, so stopping there. I will just say, don't forget, we have tonight at 6 o'clock, I think, we have a presentation from Thomas Padiolo about Kokkos, which is another way to make code running on CPU, on GPU. So I invite you very warmly to follow this talk, which is another way to do the same kind of stuff. Thanks to you. Ah, je ne sais même pas s'il y a des questions.
Hello, everyone. Hello to everybody. We hope you're not too hot where you are at and you had a good lunch. We are welcoming today our third satellite site, Bordeaux, and Victor Lederer will talk about Celia. So, Victor, are you here?
Yes, I'm here. Can you hear me too?
Yeah, we can hear, we can see your slides. Thank you very much for being here today, and I'll leave you the floor.
Thank you, Marie. So I will present Celia, centre laser intense et application near Bordeaux. The journey of Celia start like 20 years ago when the French government decided to put an end to nuclear tests. When they did it, they also built laser megajoule infrastructure to still perform simulation on nuclear simulation. The Celia was at this time only with the University de Bordeaux and the CNRS. Afterward, the CEA joins as support establishment. So in this time we got like a cluster Intel server and AMD server because the Celia do a lot of computation. The goal is latter-matter interaction, and to reach it, the Celia is teaching at university level, and also they have a strong link with industrial and medical sector. This is very important. So you can see our building. We have like almost 3,000 square meter, and we have like 11 room to perform laser experimentation. So this is an experimental laboratory and numerical simulation center. We have 32 researchers, 25 engineers, and 42 postdoctoral students. This is not bad. The Celia is mainly composed by 5 groups. They all work in parallel, but sometimes they can join first. You have the golf group is mainly on the experimental setup, and you have the IFSIA group, which is heavily used simulation code. As you can
Sorry,
see,
Victor.
yeah.
Victor, we are just on your
Oh.
first slide. I don't know if you changed it.
Okay, this is weird. I will stop share my screen and share it again.
Yes, it's better. Thank you.
Really? I don't really know where am I.
We are slide 8.
Okay. Okay. There is some latency. I need to wait for the latency. So do you see the infrastructure scene?
Yes, perfect.
Okay.
Thank you.
Infrastructure scene. This is the total workforce of Celia. Like I said, we have the gold group, which is mainly focused on experimental setup. You have the IFCA group, which mainly use simulation code. And for example, the harmonic group HXUV is focused on auto science. And if you know, we got a Nobel Prize for it recently. So on the golf group, they are trying to do like better laser, more efficient laser. They have pair Luma to exploit unique property of light and control many physical, chemical, and biological systems. They develop a new HP laser with rotating disc and cross-flow cooling. They are top 2 world performance, and they have strongly with industrial like Thales and Ariane Group. This is the IFCA group. I think I will not present all the group, but this one is important. Like they are doing plasma interaction, astrophysics, and they're also using AA to optimize the inertial confinement fusion. As you can see on the slide, at the bottom of the slide, they are using like all software, like a custom cheat code, Flash and Smiley, and they're scaling with TGCC. They have a big project on inertial fusion with the Taranis project, and they use generative AI for the inertial confinement fusion, thanks to the work of Mourad Bentayed and Jean-Luc Feujas. So there is the big picture. We have we intersect with a lot of domain, pharmacology, X-ray, dermatology. This is like a several year of work, in fact. So now I can focus on the IT service. The main mission of the IT service is to manage a cluster and a station. As you can guess, we have the ITES level security with the ZRR level, which means not everyone can go on the site. They have to sign an agreement. About our tool, like for critical operation, we're using the Proxmox hypervisor to easily run a simulation code. We can use LXA or Incus container technology to do the same, but on high test level like TGCC. We can run our custom code with Docker and Peacock. And there is a new project, like it's used to easily create new environment and to make it reproducible. So in this case, we are using GNU Geeks. It's currently developed by INRIA at Bordeaux. So to do all our simulation, we have like 3 cluster. So there is a Intel cluster, an old one and a new one, and a new AMD cluster. And we have like a great speed up switching to the old to the new workstation. So there is some software like it's better to run on workstation. Example for Ansys Fluent, and we have workstation to deploy our LXA software. We manage access to resources using several clients like SSH or MobileXterm. But the cool one is SyncLink. It's cross-platform stream desktop, so you have like a remote desktop, and you can easily access to your visualization data. So our cluster are hosted at SHM. If you know, it's hosting also the MCA Curta Mésocentre Gironde. Donc we only have one racks. So software stack. So height level, we have a Smiley, particle in cell code for plasma simulation. Octopus, like a software asking a huge amount of RAM. It's incredible. Fluka CERN, Monte Carlo simulation, and Flash Rochester. They're easy to install and easy to use because of their huge community. And like low level, we have FFT, of course, HDF5 and MPI. Some of us are developing using Kokkos. I will show you some numerical simulation. This one is using COMSOL. In fact, our colleague need to reduce the heat of some scene. This is not a huge simulation. A huge one, for example, it's a pure Fortran. And we have to solve the time-dependent Schrödinger equation. This is important because we can study and understand how chiral molecule interact. And chiral molecules are heavily used in pharmacology. And it took like 1 hour on our new cluster, and on the previous one it was 4 hours. So we have a speed up of 4. I will end with the Fluka simulation and the post-processing. So we have to study the influence of energy deposition, and we did it with Fluka software. There is also like Smiley simulation. They're asking a huge amount of time depending on the mesh, and Smiley Inde simulation. So here it is, the Celia work. I hope you have a better view on our laboratory with this presentation.
Thank you very much, Victor. It was really interesting, and I'm sure that it has interested a lot of people in the Gray Scott School. We hope also that you enjoy Gray Scott School since the beginning. How is it in your side?
I didn't attend all the courses because I have a lot of work. I try to put some colleague on it. I have one who should attend the Rust GPU courses, and some attempt the very beginning of the C++ course. But it's really nice to see a huge amount of people in this event. Yes.
Well, thank you very much, and we're very happy to have you also in this group. So thank you, everyone. Don't forget you can ask Victor some questions through Discord, and
Yes.
we'll meet at 2 for the afternoon of today. Thank you.
Bye bye. See you.
Hello again. I will continue with Fortran on GPU, and then we'll have a little presentation on Kokkos. So, Vincent, it's yours.
Thanks. So once again, Vincent Lafège from IGC Lab, directly from the Jurassic era, on bringing it to the doors of the stars. So we are back to the Fortran, as you have probably noticed from yesterday. We want to go to GPU. So we'll see today 3 ways to do so, among others. So I will start with a short overall presentation of the topic, and most will be hands-on. So as you certainly noticed, the GPU use a very large parallelism, so we want threads, lots of threads. And the 3 main ways to get your Fortran code to GPU. Okay, so older style was OpenCL, and OpenCL is C. So you would need to bind it with the C language, and it's very heavy. The nice point of OpenCL is that it works everywhere inside, even out of NVIDIA. And the modern replacement would be Vulkan, that also has the same characteristics, but it's really too heavy for what we want to do. We want to start from our good old Fortran and make it use GPU. So the first high-level language on the market that allowed this was from NVIDIA, and it was CUDA Fortran. It's exactly like CUDA for C, C++, but for Fortran. So you get extra attribute that we'll shortly see. I won't advocate this, and I won't use corresponding code for Grayscott. We'll shortly see that we can use the CUDA libraries, in particular QBLAS and QRound, in this context. Okay, the negative point is, of course, it works only on NVIDIA. What we'll, in fact, start with is directives, on, in particular, OpenACC. So they are also mostly NVIDIA-oriented. And we'll see that expressing the parallelism is not the hard point. And the hard point is to get explicit memory handling. There is also OpenMP, which is not only for multi-thread and vectorization, but allows you, starting with version 4.5, to offload some of your kernel to a GPU, to an accelerator device. So we'll see this. And we'll conclude with what is the best way, but in which we have no control over the result, using only modern Fortran with do concurrents. And it is the so-called STD-PAR, standard parallelism of NVIDIA. In fact, NVIDIA tells you there's nothing to do. Not really. So the first thing we discover when trying to use GPU is we need the good kernel module with the right kernel and also with the right GPU compute capability. So, as we will see, also with the right compiler. So you have to align a lot of parameters, and it's a lot of system installation that you have to do. So your, in some sense, hello world starts before you start programming, when you can get the NVIDIA SMI of your computer producing you this kind of result. Starting there, you know that your GPU is on and your kernel can access it. So this was an early attempt to use Vulkan in Fortran. It needed to define a lot of parameters before even trying to program something. So I did not continue along this way. It provides you access to all the detail you want. And the next step would be some CUDA Fortran example. So here you have the typical compilation line. And you have specific attributes for CUDA Fortran, such as the global attribute for the subroutine. On top of which, you have these variables, such as block dim, block IDX, that CUDA user know, as well as this kind of attribute device that tells you that these variables, this array, are defined on the GPU. So not only you need this specific CUF for CUDA Fortran extension, not only you need the NV Fortran compiler, but you also have to modify your Fortran to design where is stored your variables. And then you have the kernel call with this specific bracket syntax. So it is called Fortran, as in CUDA Fortran, but it requires a lot of change to the code. So it means that for some cases, we need to maintain the CPU code and the GPU code on different sources. So we would like to avoid this. So you will find at this GitLab, which is the same that I shown last time, the example files as well as the solution. So please give it a try. Who has a GPU? Okay. So we have images. I will send the images. So as for the last time, we have a make file that was mostly for the CPU part, with a lot of targets, and the code has not changed much considering the word cloud. So we still have all the variables defined here, but we'll read them from the NML namelist file defined also last time. So the init field has been changed to take the same definition of the drop of V as you will see in the code. Okay, the parameters are extended to the sizes. So as last time, I couldn't show you the OpenMP multi-thread version. I will correct this right now, and then later we'll move from thread to GPU, so that you can see the directive at work. on how we get some performance out of the CPU first, and then how it helps us to move to the GPU. Okay, so I took the source from Git, and then can you read?
Yeah.
Okay. So last time, we had this, a module with the setting, then among the possible stencils, we chose the ISO one. So here we put some HDF5 file into play with the dataset name of matrix. In the introduction, we read the values inside the name list file, and we write them to the output in order to check that everything is working. Okay. Then there is some black magic with the HDF5, but you can check in this other file all the definition. It's very verbose, but you can find example to call to open the various level of your HDF5, starting with opening the interface to HDF5, creating a file, creating a data space, creating a data set inside the data space, chunking the data set, deflating, compressing if the Boolean variable is set, and creating data set with the properties as well as memory for the data space. And then there is this ability to write only a slice of it. Okay, so black magic. So the initial version was very old style Fortran. We loop over the column and the line, because Fortran is oriented this way for array, and then we sum over all the cases of the stencil. So this is only setting the initial condition, putting an absence of U in the middle on the drop of V at the right, at the same place, and setting the boundary conditions for U and V. Then we have this old style routine that we may have to compare when we want to write out without using HDF5. On the main program here, allocates memory after the initialization phase, and we add this wrongly placed OpenMP directive. Okay, why is it wrong? Okay, so this main loop here is the loop over time. And this one is a real iteration. It's not any multiplication, all these, the step of this loop depend on the previous one. So we cannot parallelize it. Okay. Besides this detail, as long as you don't set OpenMP, this program should not be a problem. On the main loop is quite short. We compute the formula with these rather compact lines where we have separated the computation of the Laplacian for U and the Laplacian for V in separate array before the main loop. So we have defined maybe a bit more, too much memory, twice as much, not so good. And then we put back the result of U1 in U0, and we start again. We write out the solution, and we close. So this was the initial status of the code. And it needed some rewrite before being usable for what we want. So first, OpenMP. Okay, so maybe we'll start with a short number of steps. But in fact, it will be overwritten, so it's not a problem. We'll use this trick, which is to write to a device in memory instead of writing on the disk. In this way, we'll be able to get some speed up. But not the one we are interested in. In order not to compute the Laplacian for every case of every places on the field, we will turn to this computation here, where we compute the Laplacian with the sum of the stencil times some excerpt of the field. So we only compute it in one place, and then we use it in the same formula, but as a scalar rather than as an array. So we explicitly write all the j and I. We run over all of them. So this subroutine will compute one step of evolution. And then we update the result by writing if the logical value is right, one slice in the HDF5 file that is open. And so we find the main program that starts with the initialization of the settings of the field. We get the evolve subroutine to run over all the iterations for the number of steps. And at the end of each iteration, it decides whether to update if the number of iteration is a multiple of the intersave count. Okay, and we close the file. And we display the number of microseconds spent. So we check once more the settings. Okay, 320 steps. Will not wait in vain. So let us go to all the details of the compilation. So we first get things working on the CPU. So we ask for the debug information because we want to see in which line we have problem. We set all the warnings. We recall the compiler that if anybody forgets an implicit known, it should be punished. We ask for the how fast. We want to get the best of the native architecture. If there is some vectorization, it will be here. And we also will use any OpenMP that will be in the file. But as we have just seen, looking for OMP, there are none. So this code is pre-OpenMP. It's purely serial. Okay. And then we ask the compiler to unroll loop, to vectorize, and to display information about the optimization. We add the link to the HDF5 modules. So don't forget, in Fortran, a module file is what takes the role of a header file in C or C++. The problem, the good part is you don't have to maintain this header file on top of your source file. The bad thing is that every compiler is generating a different format of mod file. And as we'll all be moving to G-Fortran 15, it will not be compatible with G-Fortran B415. And of course, not compatible with NV Fortran or Intel Fortran. Okay, so we take the file compressed hyperslabs. The one I've just shown you, which is in the solution, which is pre-OpenMP, no parallelization. We link it and we execute it. Okay, so we should do this, but before we'll do the same thing without optimization. So without optimization, no vectorization, no OpenMP, only this. And when we execute it in the end, we have no thread. Okay. So it reads the value. We know it is going for 320 steps. Okay, and so, okay, it's already finished, hopefully. So it took 21 seconds for 300 steps. It's not very good. So in turn, we'll add some optimization, starting with OFAST. Yes. So here the optimization are displayed. You see there have been a lot of them, and we have been from 21 seconds to 1.6, 1.7 seconds. So more than 15 of speed up. And we have not been asking for vectorization, but OFAST is setting some of them directly. So do we win much by setting all the vectorization options? Not quite. So it was vectorizing without waiting for our permission. So given this, let me show you what should have been the last time result. What happens when we use directive and we move from pre-OpenMP to OpenMP? Okay, sorry. Okay, so it starts in the very much the same way. Then in the evolve subroutine, we have this notation. So this is not an OpenMP directive. This is an OpenMP directive. You see the comment, which is the exclamation mark, the dollar, which combines with the comment to tell the compiler, when you ask for OpenMP compilation, take this into account. But this code on this side, the OpenMP version, is in fact good to be compiled for a sequential version. So inside the iteration over all the steps, so when sorry, before going further, when you have this notation, it means these lines will be compiled only when you are compiling OpenMP. And in this case, it will use OpenMP lib module, which allows you to have some functions such as this one, OpenMP get thread num, that will tell you the number of the thread that is running this code. And here you see also that this standard if will only start when you have the OpenMP compilation option. Okay, so we define what is inside the time iteration loop here as one parallel region. So it starts here and it ends at the bottom here. It means that from this point, you have as many threads as you will define. So you can define it in the program. You can define it with an environment variable, as we will practice regularly. And these threads will live from here to there. And of course, it's up to the OpenMP implementation to keep a thread, a pool of threads, so that you don't have to recreate them at the end. You only pick them back when you enter the parallel region. And now we define the easy part, which is saying that the following loop has to be separated among threads. So all these 1078 loops will be separated among threads. The next level here is that we ask for SIMD of the inner loop. We will try to vectorize whatever occurs inside this inner loop. So now for the less obvious aspect. Here we have to declare that some variable will be shared among threads. So it's easy to read them from a single value, but it means that if you have a write variable inside this shared region, you can do stupid things and overwrite things that should not. So you have to think about not overwriting with one thread what you are writing with another. So our two fields, U0, V0, on the next step copy, U1, V1, all these fields are shared among the thread. End step is a constant. Iteration is a constant among the threads. And I and J are the loop indices, so they are shared. Then we see also that we have this private value that are not the same in every thread. You get a copy of the, you get an independent space for LAPQ and LAPV in each thread. So we know that we will not overwrite the, yes?
Can you explain a little bit about the SIMD alignment and what is the safe len? I didn't know that OpenMP is also responsible for vectorization.
So this tells the compiler that U0, V0, U1, V1 are aligned in memory. So it has to take the proper steps for this. On the length across which you can safely vectorize will be as much as 64 bytes.
Mm-hmm.
But, well, of course, it would be really in the best case with AVX 512.
This is hardware dependent, or
Is it?
This is hardware dependent.
Yes,
yeah.
Absolutely. So, welcome to vectorization. We introduce a lot of dependencies. Okay, so here we have a very classical step, which is checking that the so-called master thread is running, and only the master thread will display something. So, okay, except for the final message, we have the same thing. So now we will compile with a lot of vectorization options. and a lot of optimization options, everything that we want, including the OpenMP setting that will trigger all these directives. So we should always start when multi-threading some Fortran by testing that it works for one thread. So we should expect the same result as sequential, more or less. Here we go. And same number of microseconds. Okay, that's good. So now we can check that with two threads, we expect a speed up. Not so much. So maybe it is time to play the game with a bit more work to do. Okay, so you can see that the wall clock time is only 10 seconds, but the user time is twice as much because the two threads have been working. Okay, does it scale? Let's move to 4 thread. In fact, it scales well. We went from 10 seconds to 5.6, not too bad. Maybe it's also time to give some much work to, a bit more work to do. Okay, so twice as much, and we went from 5.6 to 11. It scales well. And this machine has 8 cores, so we should expect the same speed up of 2 once more. And this is the case. So there is certainly some overhead because the total CPU time went from 45 seconds to 49, so almost 10% is spent. So we are now ready for the full scale image. So as you can see, all the cores have been working. And we have 32,000 images in almost 32,000 microseconds. One step by microsecond. So this is nice, and now that we know that the CPU can do this, we'll attempt to do the same kind of thing with the GPU. So you can take in solution the pre-OpenMP file, and instead of using OpenACC directive, we'll try to use instead of using OpenMP directive, we will use ACC directives. So while you look at the aspect of the ACC code, I try to reuse some extra vectorization options. Okay. So before this last multi-thread vectorization compilation, you can check for the various flag of your CPU using this /proc/CPU info. So it's a bit verbose because you have a lot of cores and you have the repetition of all the flags for each core. And you see that there are a lot of them. It's a bit difficult to know what it means. FPU, okay, there must be some FPU somewhere. And then you see that AVX 512 has a lot of declination. It appears in 1 or 2 dozen flags. That maybe don't exist on all AVX 512 CPU. So collecting all these specific flags, you can tell your compiler that all of them are here. Will it help? Let's see. So we see that half the core are running. Of course, we don't send the hyperthread one. We don't want to lose time. And then we have 23 seconds instead of 31. So please be cautious with what exact kind of CPU you have. Telling AVX 512 is not enough. Go into the detail and the compiler will help you. Okay.
Sorry.
Yes?
Is it possible to copy your comments? Because it's a bit hard to
Yes.
try to run everything at the same time as you.
Sure.
Because it's quite long every time. So
Should I share it with the Discord?
yeah,
Yes.
thank you.
Okay. So, okay, for people starting with the OpenACC, now we'll have to use the NV Fortran compiler. But before leaving the wonderful world of CPUs, I will try to look at the other big compiler, the one from Intel. So for those of you who have the Intel compiler installed, this is the way to ask for it to be installed. We check ifx minus version. Okay, this is the recent one. Okay, so I share this for those interested. So here we see Intel compiler, debug option, optimization, all warning, implicit none by default, start OpenMP, SOX. Okay, we start with only the default AVX 512. And as I mentioned, each compiler needs a different module. So we go to a different set of include compiled explicitly for Intel. For the HDF5, then we use the HDF5 library designed for this case. And we'll start with this. So as we'll be looking into a different libraries than the default one, before the execution, we set also the library path to look for the Intel Fortran library. So as we see here, we have 50% of the core that are used, but in this way, we don't have the other core. So what went wrong? We are 10 times worse. Whoa, surprising. So I will provide the same detail of the vectorization. This is surprising. So, okay, 31 seconds, not better. Fortran made a nice work out of it. So, anybody has an idea for the OpenACC directives? As a reminder, we would use OpenMP in this way, defining a parallel region and detailing what loop are to be parallelized and looking for the variable that are shared and the ones that are private. So let's look first at some GPU examples. So you can find this GPU example as a GitHub gist. I share the URL. So we have a module with the common data. They also have two copies of one field of the same size. And they start with very basic initialization. So you have limit condition for the first and last column. And the first and last line are set to 0. So the ACC directive looks very much like the OpenMP directives here. We specify which data are copied from the CPU memory to the GPU. So you'll get a copy of A at the start of the parallel region. And you will create, which means create on the GPU, on the device, your copy anew. Then, as long as some error is greater than some fixed value and the iteration do not exceed some other value, we call the Jacobi relaxation step, call A, we compute the error, it's called error A, and we update A. And then we have the end of the parallel region on the GPU. So the results are written on Jacobi.dat file, and you find routines there, use common data. And this defines the parallel loop with a reduction. Well, in fact, this will have no effect because there is no max value, no error value computed with a max reduction. This is only this kernel that is split across loops, across the first layer of loop, and then the second layer of loop. And as you have already seen with other languages, this is common for GPU to split with 2 layers of loop. So here, update is a copy of ANU into A, and this is done with the same structure of ACC loop. So if you can, you should remind only one part. Here we don't have the ACC end loop at the end, contrary to what appears in OpenMP. And here, in this parallel region, we have, in fact, a reduction of the variable error, which is the max across all threads in the parallel region. So we only keep, in this way, the max error across all the threads in the field. And in the end, we write it. Okay. So when we try to reproduce what we just learned, okay, things change a bit. So on your left, you see the pre-OpenMP not parallelized program. On the right, what it becomes when you use OpenACC directives. Okay, so maybe let me compare it to the OpenMP version. So the first occurrence of this ACC region defines a data region, not a parallel region. So we prepare data in advance before declaring the ACC parallel regions. So in the main routine, we go from here to there with data U0 and V0 that are copied from the main, the CPU, and we create U1 and V1 on the GPU. So the real thing will be here in compute. So in compute, we apply the stencil kernel for the computation. Sorry. And now we see some new construct which tells us that we will collapse the loops, the two loops for afterwards explicitly. But, okay, beside this, you recognize the same code inside the loops. For the CPU and the GPU. The same goes for update. We collapse two parallel loops. And, sorry for the French, but this was a previous attempt here where I just defined a parallel region and I was hoping that the compiler would make the best out of it. So as you can see here, this is simply an array copy. There is an implicit loop in this expression. But in fact, the compiler couldn't make any performance out of this. That's a bit sad. And beside this, not much changed. Beside the end message. Okay, so now we'll have to compile this. And by default, I don't have the NV Fortran here, so I will set the proper variable for the NVIDIA toolset here. I source the file, and now I have this last NV Fortran version. Okay. Any question?
I don't want you to. You cannot. I'm not using English.
Okay, so for the OpenACC compilation, we go into the detail of the, yes?
So there is a question, why do we define the compute function as a subroutine when we have just two loops? Is there a particular reason for this or just?
No. In the case of such a limited program, we could have everything in the same file.
Yeah, so just for clean code.
So yet another compiler, yet another set of options. -G is common. NV Fortran goes to -04, a very aggressive optimization. You tell the compiler that you want the accelerator, and that your accelerator will be the one with the native compute capability, CC native. So you could compile for some other machine by specifying the appropriate compute capabilities. You will be asking for information, all the warnings. This mdcl-check is in fact the implicit known command, flag. And as it is yet another Fortran compiler, we need yet another module for the HDF5 library. Okay, so before executing this, I had better move to the solution. Okay. So the file is here in the examples, this file here. And then we compile the ACC that we have just seen, and we link to the proper variables. So the optimization options are very verbose as well. It tells us that some loops are not fused and some are not vectorized. This occurs in the setup file subroutine, so maybe not the most interesting one. Write slice is doing I/O, so it's not operating on the GPU. Okay. Read slice, that's the same. The evolve routine, and in particular the compute routine, are the one of interest. So implicitly, he decided that the NX and NY variable will be copied and will have private value for each thread copied from the starting one. And here is the expected NVIDIA GPU code generation, and you get all the details that tells you, we just asked for ACC loop, and he told us, okay, I take gang vectors of 128 on top of our request of collapsing two loops. He's generating the data movement, copy out of V1, the implicit copy in of V0, U0, and also the copy out of U1. Okay. 14 seconds, it's rather good compared to, yes, we were at 16 seconds with G-Fortran. So CPU with good vectorization compares to this GPU. So maybe we can improve things on the GPU side, but we are playing on the same level. And up to now, you see, it has been a couple of directives thrown upon almost normal Fortran code. So compared to what kind of effort would have been needed for Vulkan or OpenCL or others. It's rather nice. Okay. So maybe we should be looking for some other way to use the GPU. Or before moving to OpenMP, we would like to see what happens here. Oh, sorry, way to get it bigger. Not so much bigger. Okay. A bit bigger?
For me, it's okay.
So, as the common wisdom we get from the start of this school, we want to profile all our applications, and the same stays true for the GPU. Okay. So this is here that I should set environment variables. Okay. So the characters are big enough, but the details are tiny. So we see the span of the 14 or so seconds described. So we want to go into the detail. And we zoom out. And we see details at the level of the at the detail of the level of the millisecond. So okay. So we see that we have two kernels. Which is the compute on the update. So putting the two kernels in different routines help us understanding which is which. And in total, the GPU does not lose much time. You see this small gap between launching two kernels. And alternatively, it is going from the compute to the update and back. Okay. From this, do you get any idea to improve the code? Okay, we should keep in mind the main line of the talk is that computation is cheap. Memory is slow. And can we not get something better from this update? Because this is purely copying some memory in some other place. Whereas this is really computing something. So what I suggest is we get inside the update instead of the copy, the same computation but applied to U1 that will fill U0. and correspondingly for V. Okay, so now we have the same ACC parallel loop collapse. We have to define the Laplacian value. And we'll have to change something in evolve because we only need half as many steps now. So there should be a test because we expect that the number of steps is exactly an even number. So to compare to the other iteration are twice as fast, so we'll display things to compare previously. And during the update, we should write if twice the number of iteration is a multiple of intersave count. Okay. So here it goes. Not bad. So as a reminder, we started with almost 14 seconds, and now it's only 8. Almost double speed up. Okay, so
But
yes?
the update is not even half the whole time. How do you get
Yes.
double speed up?
So
By cutting the time on the update in half, basically.
okay, here we see, I have not yet changed the profiler. So we are on the profiling of the old one. We will go into the detail. But in this profiling, you see that we spent on this kernel 257 microseconds. So this was the compute kernel. On the update kernel was 153. So some aspect of even the compute kernel is not purely computation. We move data.
Yeah, yeah.
So we could not expect completely a factor of exactly 2 because we have to spend some time moving data around. Okay, so how do we restart it? So same project, and now we restart. Okay. So now it's 50-50. We have the compute and the settings. Let us zoom somewhere here. Okay. this compute here for the update, which is computation 266 microseconds, and here for the compute 266, 267 microseconds. So we have a very symmetric situation. So time for a break. So we'll be back at 16.
I'm glad you got it to work.
Back to the Fortran. Okay, so we have seen how to extract a lot of performance from OpenACC, which has been the main actor for vectorizing and GPUifying your code in Fortran for a long time, in Fortran, in C, C++ as well. Can we do better? Can we do otherwise? So up to now, we have seen OpenMP as a way to multi-thread one's code. We have seen OpenMP as a way to vectorize one code, but there is also a way to GPUify from OpenMP. So how does it look like? So we'll compare the OpenACC version to the OpenMP offload version that you can find in the solutions. So it will be with NV Fortran as well. And when you compare, we now speak of target data with maps to and maps from. So we define a data region first, as we did in the OpenACC world. So as you can see, it's only a direct translation from this part. Instead of copy, you have map to, and instead of create, you have map from. And you specify the end of a target data region. And then for the parallel region, we have a target teams. So the syntax is similar, but a bit different. Okay. So we have been modifying this OpenACC version, and we will check that OpenMP behaves in a similar way. So if we see, okay, the first line was with information about acceleration, and now we'll be looking for MP. So not much change about the syntax. We have this upload code, and here we'll be looking for what is in example. And here we go. Target activity. Okay, so we have information similar to what we had with the OpenACC code. The vocabulary has changed to teams, and but the information stays almost the same. And we have almost 14 seconds, so it's really comparable with OpenACC. So we should check what happens. So now the name of the executable is this one. Okay. So let's start. Okay, so 14 seconds. Really similar. And we find a close alignment 1/3, 2/3, as we had with the first OpenACC version. And here you can see the compute and update the same way with 250 microseconds for the compute and 136 for 137 for the update. So we'll play exactly the same thing, the same trick as we had in the other version. We'll play with half the number of steps. And we replace the update by a compute in reverse. And when writing, the same thing. Okay. Ah, yes, I forgot something. Declaring these two local variables. Okay, 9 seconds. Almost the same as with the accelerated OpenACC. So we start the profiling. And we get used to our code with this 50-50 split between the two kernels that are morally equivalent. And okay, no surprise. So 250 microseconds and 250 microseconds per kernel. Okay, so in this case, OpenACC, OpenMP, basically they are equivalent. But it's nice to have multiple tools in one toolbox. Can we do even better? Even better.
Do we make some unnecessary copies?
So yes, we are already almost 35% better than the CPU with vectorization at its best. It's not bad, but at least can we do simpler? You see, writing all this syntax. Okay, when it is done, it's not a big deal. It's no big fuss, but a lot of documentation has to be read. You have to practice. Start simple, as Pierre always says. Take Adamar product and practice your OpenACC, then your OpenMP on this before simulating the weather for the planet Mars. Some steps. Okay. So, as I mentioned, so we have already seen, this OpenACC way, this OpenMP way, and now we will explore the big claim of NV Fortran. NV Fortran tells us it will auto-GPUify. We don't have to do anything. Even better than directive. Okay, so let's look at this claim. Okay, the comparison is not quite nice this way. Let me make the comparison with the pre-OpenMP maybe. Okay, so we have the evolve routine, and it used to be iteration over the number of steps. So, okay. So in the std-par, I've learned my lessons, and I've already distributed the two kernels, the one that was previously evolve and the one that is compute. I put the same in the. I put the two in the same routine, so I already have this n step over two loop of time, and you see, in old Fortran, you would have this kind of loops, one loop per variable. And in modern Fortran, when you have concurrent loops, when you call only pure function, you can let the compiler decide for you. You give all your variables here so that it will select in the nest of loop what is good and what is not. Here, in old Fortran, so you have the first loop over the time, and then the two loops over the column and the rows. And you had to select that this loop over the columns was the outermost loop, because data are contiguous and you want your inner loop to take data as close as possible from the other. So the compiler can decide to vectorize the inner loop because data are contiguous. Now, we let all the dirty job to the compiler. And this is the promise of Fortran. I translate formula. This is my job. You do the high-level job. I select if I goes before G, J, or the reciprocal. Okay. So for a long time, we also have replaced this initial, these old loops where we had to initialize this aggregation variable and sum the product of the stencil. Now, this is a modern Fortran expression. Let the compiler do the dirty job. Do the dirty job. Okay. So this first part, compute from U0 to U1, B0 to V1, on the other, that's the reciprocal part. And then okay, this something is not quite right. Because we will have only, okay, intersave. Okay, here the count of intersave loop is half the number of intersave count. So here we compare the number of iteration to half the number of iter count, while before we are comparing to intersave count, and here it is intersave loop. Okay, tiny detail. Okay, so this was the old evolve. So you see this, this program on your right. There is no directive, no OpenACC, no OpenMP. So we should start with some std_par. So the initial claim of the do concurrent loops was to be able to parallelize. So it started in Fortran 2008, do concurrent. So GPU were not really a thing at that time. So the claim of NV Fortran is by adding this standard parallelism, which means do concurrent, will be multi-threaded. And then we can accelerate, we'll show information about the acceleration. Okay, all the standard options. We take this std_par that we have just seen. Okay. Does it work? So this one has no temporary writing, so we will just be looking at all 16 core being lit. So the compiler has multi-threaded automatically our code written with nice modern Fortran. The most bounds for the bugs. Or it takes some time. So I share the compilation line. Okay, so finished. Well, 20 seconds for the system, 1 minute 13 seconds on the wall clock. It's not quite good. Can we do better? We had only 20 seconds before, on the CPU, I mean. So maybe I should use only half of the threads. Does it use OpenMP num thread as a set? Let us check. No. Not so easy. Okay. So can we improve it with the vectorization options? So the interesting part, if not so interesting, is, okay, we use all the CPU to 100%, but they don't work efficiently. The elapsed time has not been at 30 or 20 seconds. So does it read the vectorization options? Not this one. well, not a significant change, as we have, yes, 114, 115 instead of 117. And the worst thing is we spend a lot of time in the system. So probably this hyperthread thing are really what makes us in a really bad situation. So the vectorization improvement has not helped us. So how do we limit the number of threads? Okay. So the documentation tells us about ACC number of core. So here the overall CPU is 50%, so it looks right. And we see some of them at 100%. Okay, so okay, so the system time has reduced, but the overall elapsed time has not changed much. Surprising. Okay, so looking for, so we have seen the thread going from one core to the other to spread the amount of heat produced.
Excuse me?
Yes?
We're trying to reduce the number of threads because they're trying to run concurrently on the same course, or
So
what is the
when you launch a 16 thread, which occur naturally, they were in hyper-threading mode. So
by default,
by
you
default.
have like 8 cores, which can
Yes.
okay.
But we have only really only 8 cores. Okay, so should we try to set the cores that are allowed to execute? Okay. So it be this syntax 0, 2, 4, 6, 8, 10, 12, 13. C'est bon. Okay. So now we expect, you see, only the core 0, 2, 4, and so on. The tasks are set only to given cores. So we should not lose time moving from one core to the other with the possible memory cache loss at the time.
Are these ones hyper-threading now?
So I should check if 0 and 1 are related to the same physical core. But in principle, I will have 8 physical core here. In this
Yeah, it's
context.
probably like you say.
Better. Ah. Slows down. Okay, well, it's worse. 2 minutes 15 elapsed, 8 core used at 100%, twice as much as before for the CPU for the system usage. So this was not a good solution. Okay, what is the CPU list? Sorry for the French.
Could it be that hyper-threading is actually good in our case?
So maybe we should give a try to the OpenMP version that we started with. See if task set helps or not. Okay. So let's check. Okay, so we have found that Fortran was the best on CPU up to now. How fast, machine architecture native. General loop, prepare width. The wall is twice. So now we are not in the same directory. Okay. So to keep track of the initial time, and then you see the CPU, the core are changing, the one which are at 100%. Or maybe I did not provide the right list. So 23 seconds. Okay, best CPU time. So now I want to task set the same CPU list. Okay, so maybe I got it wrong on I should not task set all the even core number, but only the core numbers from 0 to 7. We'll soon now. Yes, this must be it. So I should have read the documentation. So you see, instead of 23, we are at 29. Okay. Maybe it's even more complicated than that.
You forgot the file.
Not at 100%. Okay. Yes, indeed, the result is really bad. So
You forgot one CPU.
yes. So I already told you to look for cproc/proc/CPU info. And we'll be looking to processor. Okay. And we would like physical ID or core ID. So processor 0, processor 1. We look for physical ID. So processor 0 and 1 are linked to the same physical ID. So this was the initial guess, which is the ID 0. Processor 2 is also related to physical ID 0. Okay, so yes, there is only one processor. So if I look only for physical ID, I get 0 each time. Okay, we have the same processor. So we'll be looking for core ID. So the first processor is core ID 0. Then the second is core ID 1. The number 2, which is the third, is core ID 2. 3, 4 is 4. 5 is 5, 6 is 6, 7, and then back again. So in principle, the last attempt should have distributed 0, 1, 2, 3, 4, 5. As you said, I missed one. Okay, looks better. Don't know why. Okay, it's finished. So, 24 seconds. Remind me, without the task set, was the same, no, 23, something like this. So just checking, but okay, so will it play for the STD par? Okay, so it's better not fix them. So, as you see, we are trying to guess, but it could come from vectorization not done in the same way by NV Fortran and G Fortran. I've given a lot of flags to the compiler, but it's a dark science. We have to read a lot of documentation. Okay, so here the system took almost nothing, and we went back from 114 to 111, so not very significant. So comparing the 22 seconds to the 71, there's a clear advantage for the explicit OpenMP in G Fortran compared to NV Fortran std_par. So it's a work in progress. At least we had some multithreading without doing much. We did not specify which variable were shared. We did not specify which variable were private. We did not tell where did the parallel region start, and so on. So, okay, it's far from good, but it's not bad either. Okay, so now for something we all expect for a long time, can we use the same thing, but for GPU? Let me copy it. Okay, so let us be back to the topic of today. We call NV Fortran. We want it to accelerate with the native compute capability on using standard parallelism, which is do concurrent, ported to GPU. We want information about what acceleration are done. And we ask for fast result above all. Okay, we check the example HDF5 library on the same std_par that we were compiling on multi-core. We now compile it on GPU. Not bad. Nine seconds. With only do concurrent, no OpenACC, no OpenMP. We let the compiler perform its magic. This is the promise of Fortran. Okay.
This is on CPU, yeah.
This is on GPU. We will look at the Okay, so let me provide you with the corresponding copy. Okay, so should be this one. Let's move to the Insight project. So to compare, here the full project was spanning over 9 seconds or so, with OpenMP, while the OpenACC was about the same. Okay, so we are a bit better. And we start a new run now with the auto GPUified version. Looking for the details. It was more equal before, 50-50, but it's not very far either. So we have the kernel 116 and the kernel 1.9. They take 270 and 270. So we had something in the order of 250 with the previous one. So we lost some time, but not so much. So let us check again the time of OpenACC. The time of the OpenMP offload. Okay, OpenMP is not better, but OpenACC on the the STD par are on the same level of performance. Okay, so is there something to be improved? Okay, so something has changed in this last run, because we have one memory operation in progress here. GPU utilization for runtime library trace. Okay, great. We have some IOCTL, some weight, some CPU utilization all along. Some runtime of the OS. Okay, so here it looks like there is different behavior. Well, okay. And here we have some wait time during the OS runtime, the library. Okay. Any idea? What should we try to improve? Okay.
I didn't understand. How do you get the CPU time to 9 seconds in the last two runs? Did you change the length of
the execution time of the OpenMP1 here?
Yeah, how did it become 9 seconds from 22?
Okay, so this one is OpenMP offload, and not the OpenMP multithread. So the last OpenMP that was run here was the one that used OpenMP target on Teams. So it plays not as usual OpenMP on the CPU, but it makes the GPU work. On this, it's almost as good as OpenACC. It's not very different, but okay, not as good.
OpenMP Teams makes the GPU work.
Yes.
Okay. But it wasn't. It was slower.
A bit.
Okay.
10%, less than 10%. Okay, so we are computing things. We are computing things quite fast because we had 14 seconds with the CPU. We have 9 seconds, 9 seconds with the GPU. It's rather good because we take less than about half a millisecond for each step. So as we want to have one image, one frame, we have a total of 32,000 steps. That makes 1,000 frame for the movie. We want 40 seconds of movie in the end. So they will be played. It will take less than the 40 seconds of the movie to compute the movie. So
you can do it real time.
Deal. We have the real time either with the CPU or with the GPU. But is the result good? Because we measure the time, but we may want to see the results. Okay, so something we have not done yet is save the result of the computation. So maybe we will address this now.
Isn't it 9 seconds also? How much was it?
So in the name list, So we had a file here. So we were running the file with no name list. So the code took the default value. But each time we ran it, we had this error. Okay? So this program is fault tolerant. But let us have the right configuration file. Oops. Yeah. And now we will ask to get the result. Okay, so we don't know how much it will take. So we check here that so we'll check that the okay. Where do we write on here? You see, I decided to put the file into memory. So we start with this to see how much it takes to copy from memory to memory. And later we'll see what it takes on a real hard disk or NVMe. Okay. So 995. It doesn't take much to write in memory, and we check. Okay, we have the file in place. It's about 8 gigabytes, so it's correct. So, now that we have the file, okay, we'll try to write it in the current directory to see the difference. Okay, so 1035 instead of 9 something. So memory is faster than disk, but not by much. Okay, let's check that the two files.
For how
have-
much did you say? 8 gigabyte? 7.8?
Okay, let's check.
Yeah.
Okay, same size. Do they have the same signature? Ooh, something has changed. Maybe it's not a big deal, but let's have a look into the file. Okay, so we have the structure of our result. Sorry. Can you read?
I can.
More or less. So we have 1,000 image of the required size, and the data type is floating point with 32 bits. So this is okay. Okay, so we look at them as a spreadsheet, and we will be looking after the middle of the process. So, okay. No. 8 will be dimension 2. Depth will be this. So we cut at a given depth. And we see a lot of 0. So many 0, but we are on the border. So we want to look more in depth. So we'll look about the middle. So here we see something. So there is a sea of zeros for V, and there is this front of value that you have seen the other day. And the value you see here, something 10 to the minus 38, should remind you something.
There are others around the 0.
So in fact, this is not the smallest float possible. 10 to the 38, something like this, is 2 to the minus 127, okay? So let me check. So what is the log of 10 for this? Oh, 10 to the minus 38. Good. About half 10 to the minus 38. But this is not the smallest number that you can represent on the GPU, which would be on a, I mean, not even on a GPU. In IEEE, we could have denormal or subnormal up to 10 to the minus 45. But we don't see this wave of subnormals. So it gives us a hint that the GPU has been truncating the value for us. The GPU, maybe with some default option in the compiler, has decided there is no subnormal. It makes a hard cut. Is it for saving speed? We should read the documentation of NV Fortran and know about this option.
Is it possible your visualizing software is just rounding things up?
It's another option. And okay, we see that, okay, this. Okay, here the digit reach the end of the. Okay, so when we go more inside, we have something to the 29, minus 10 to the minus 29, minus 16, minus 17. So for the physicist or mathematician among you, with such small value, the linear approximation for the Gray-Scott equation is possible. So you can write it on owing to the cylindrical symmetry of the problem, more or less, beside the size, the shape of the spot, which is a square. But you will extend the equation with Bessel function, the cylindrical Bessel function, and you can see what is the typical wavelengths of the equation, and you can fit, you remember the two front wave of denormals that we had, and they were separated by 23 binaries, 23 power of 2, because between the smallest denormal and the first, the biggest denormal, you have 23 bits of the mantissa. And it corresponded to this exponential decrease of 16 bits could be computed with the linear approximation. So even when the equation looks horrible, mathematics can help you see some of these things. Okay? So we have data. They have more or less some expected shape, but we cannot really see the interest of the data with just this. What we really would like is to extract images from this solution. Okay. Where is it? So Fortran is not quite famous for graphical display, but we might do something. Okay, so before displaying things, there's a question nobody has asked. We have been using a hierarchical data format, which looks like some heavy piece of software. And why not save it directly in binary? What could go wrong? So, so if we look at the initial code, there was this impure bright solution. So impure routine means they cannot be put in some do concurrent loop. And they are impure because they have I/O. They have input-output. So we'll take it on board. And then in the main program, this is the logical unit of the output. So we'll put the data in a binary file with unformatted. When you use unformatted, Fortran will take the format of your local machine. So you have no guarantee that from one machine to the other, you can share the binary data. The endianness can come into play, but it should be in principle the fastest way to save data from Fortran. And instead of, okay, so instead of writing to HDF5, we'll write the solution in binary each time that we would write a slice here. And we write only V at the end of the file. Okay. So we recompile with std_par on GPU and we execute. Ah, okay. Yes, I'm not in the right place. Okay, illegal IO specifier unit. Line 211. Yes, because I've added something that you practitioner of Fortran should do. So when you use some external module, please add this only clause that will limit the visibility in the module. In this way, you will limit hallucinating about some function coming not from the right module. Maybe write is not so good. Okay. So 25 seconds. On the disk compared to 9 seconds on the memory or 10 seconds on the disk. So even if write is a very simplest way to output data, a lot of cleverness has been put into HDF5. So think about it and propagate the good news. Yes, there is maybe something in modern Fortran. Input-output, we can maybe send them in a fire and forget mode. So let me check.
Are we checking whether the GPU is rounding the subnormal part? Is it cutting it now, or are we doing something else?
So from what we have seen in the HDF file, it is cutting them. Anybody looking in the documentation of NV Fortran? People in the Muppet Show getting some idea about FTZ? Okay, so I will be looking for the modern Fortran, the modern way of Fortran about writing data. Not good. Okay. So is it possible? So we have a lot of options here. So NV Fortran is good at optimizing your code, but it's not following the cutting edge of the norm. So something that exists, yes. Something that exists in the documentation may not exist in NV Fortran. Okay. Okay, so the error occurs at both levels. So maybe give it a try with other compiler. Here it would come into play. So, okay. First lesson, we want to have HDF5.
There is some flag M no flush Z.
Okay.
But,
So let me get the
this is on Intel, right?
Yes, but I've been modifying the code for trying the right interface instead of the HDF5, and if we want to compare the result, the HDF5 will be better. Okay, so now. So yes, by the way, yes, the binary file is also 7.8 gigabyte. So sorry, would you mind?
I'll post it in the.
Repeating the option
I
minus.
just posted in Discord in the channel.
Ah, sorry.
Or maybe this one.
Okay,
also, not
I
sure.
get it. So no flush Z. Okay, so let me also put it in memory so that we don't lose time. Okay, so 10 seconds.
I guess it should take longer now. Should it take longer now if it is not cutting the signal?
Yes. I should, to be exact, I should compare without writing both things on maybe not much, but we'll see. Okay,
Yeah, but
so
also the output file should be bigger.
well, a float is a float. 0 takes the same size as.
Yeah.
Yes, you're right. I did not set the compression option. So with HDF5, you can decide or not to have compressions, and you have a lot of options. But last time I tried, I was losing more time than
gaining.
So, okay. As we are dedicated on winning on the time issue, Okay, so let us look at this image. Sorry. No, it's not the right one. Sorry, I have forgotten to dimension 2, and I will be looking at middle of the evolution. Okay, so the numbers looks very much the same. Okay, so not quite a proof yet, but something else must be at play.
These are these two flags, m does and m flush z, and we have to play with whether it's a null or m null does, m null flush z, but I don't really understand how they work. I just speculate.
Okay.
I wrote in the Discord. If you want to try them. I wrote in the Discord
Okay.
if you want to try them, but
Okay.
I'm not sure.
So now we have the two options. We start once again. Okay, sorry, I forgot the space.
Which NVIDIA HPC SDK do we have?
25.5. Okay, so the time stays similar. Where is this one? Okay.
I posted the link where I read this, but
Okay, so yes, there is some easier solution to compare. We'll take the CPU version, which is not bad.
yeah, what does it talk?
Okay, so if we want to take this one, it will write it out. So I just check quickly. For this, and it's written in the same place. Okay. So when we check the image has just been produced, it's also 8 gigabytes. Show data, display this way. Okay. Okay. So now we clearly have a problem that might be related to the display option. Okay, so
Can you see the binary of the output? With some hex editor, or I don't know.
So I have not enough practice, but I will be looking for it in the coming times. Okay, so maybe as time is running out on I will just flash the so these are not the results from today. And I will put the Fortran program that builds the image, and then I use the M encoder to produce the following movie. But except M encoder, this was last year result. Okay, the colors are not the best one. So this will be it for Fortran on GPU, and I'm ready to take any question.
Question? Was the GPU speed up as fast as expected, or do you think it can go faster?
Well, so you have seen in the profiling program that there were some small slices of time, some microseconds that were maybe lost. Pierre will tell you that I've certainly lost it, as he could go faster than me. But I could have this STD-PAR result with a lot less effort, which is also something.
Yeah.
So yes.
But mostly it was up to...
One of my goals was to produce a CUDA Fortran version, because CUDA is considered by most as the fastest way to implement something. I mean, as the fastest binary that you will get out of your code. So here, this is not purely a technical choice that was made. It was made so that a beginner can take this Fortran. This is Fortran that first grade student can understand. Then you tweak something, and with STD-PAR, you almost tweak nothing, just the options, which is some work we have seen all together. And from there, you get your code working on GPU with no effort, almost.
Yeah, this is why it is interesting whether it's making, how much use of the GPU is making.
Okay, so you have seen, I did not enter into detail of Insight, but you really have to look at it. If you don't look for your profiler, you will not know what really happened. And then when you see some things, okay, is it a problem? What does it mean? So you have to somehow practice it. So have a nice Fortran.
Thank you.
And maybe also to add something, with Fortran, you have also access with STD-PAR to all the kernel for the mathematics, and their parts are also on GPUs. So if you want to do matrix multiplication, stuff like this, all these kernels are supported.
Yes, I didn't show the Kublas interfacing, but this is really something to play with. Okay, so I will try for the last line what is proposed by Sébastien.
I'm not sure it's for...
We will soon know. Okay. So maybe on G-Fortran. Okay. Not this one.
Should I start? Okay, so my name is Thomas Padiolo. I work at Maison de la Simulation as a CA research engineer. I work on Kokkos. I'm a Kokkos developer. And this work is also presented by the SEXA team, which is a team at CEA that works on Kokkos. So Kokkos on GPU and actually also on CPU. So why Kokkos does exist? Well, in the HPC community, we're facing some few challenges. Among them, we are facing hardware diversity. With the arrival of the exascale, this led to the introduction of GPUs on supercomputers. As you can see on the right, on the table, you can see the first, the most powerful supercomputers from the top 500 ranking. For the rank 1, we have El Capitan, which is equipped with AMD GPUs, actually APUs, the AMD MI300A. The second one, Frontier, a bit older, is equipped with discrete GPUs, MI250. At the third position, Aurora with Intel GPUs, and NVIDIA GPUs for Jupyter, which is a German supercomputer, and the last one from Microsoft Azure with Hopper NVIDIA GPUs. So we have these different vendors that equip the supercomputers and all provide different technologies to target them, either CUDA, HEAP, or Sycl for Intel. And this can lead to code duplication in some cases and to support all of them. So the need is to have some API that can target all of them at once. And this is why this is where Kokkos comes into play, to offer some performance portability, a single API that will allow us to target all of them and simplify the work for developers to target all the GPUs and even CPUs. So what is Kokkos? As I said, it's a modern C++ library for that targets shared memory parallelism. So it does not support by itself distributed memory parallelism as you would do with MPI, for example. And it targets data parallelism. So when you want to execute the same instructions on different data. It heavily uses template metaprogramming and function objects or lambdas that you have already encountered. And it aims also to follow the C++ standard. And actually, it also contributes to the standard. And as a note, the next version, the version 5, will support as a minimal requirement the C++20. So the goal is to support the GPUs, of course, so AMD, NVIDIA, and Intel GPUs, but also to support multi-core CPUs. And all of that using some existing, what we call backends, that work well on the different architectures that we support. As for the contributors and developers of the Kokkos library, it originally started with Sandia, where actually Kokkos was part of a bigger project called Trilinos. It was then extracted to, as it could be seen that it could be useful for the projects. Then the Oak Ridge National Laboratory joined the effort, and more recently, the CEA in France joined also the main developers of Kokkos. There are many more developers that are not listed here. And it keeps growing, also related to the that now it's part of the Linux HPSF Foundation, so the High Performance Software Foundation that has now 1 year. So let's dive into a simple example. So on the left, you have a sequential pure C++ code, so the main function, where we want to initialize a two-dimensional array. So let's say a C++20 example. We have an array of 2 dimensions, one that is where the size is known at compile time, so that would be the nvar variable, and one size that is only known at runtime. And then we allocate some data, some integer data here with the new keyword. And then we initialize it with a sequential for loop that will loop over the runtime dimension, and where we initialize to some value the array. Note that in this case, we do the linearization. It's a two-dimensional array, so we allocate one big one-dimensional array in memory, and we interpret it as a two-dimensional array by linearizing ix and here these anonymous variables. This example on the left only works for CPU as such. And on the right side, we have a Kokkos version of this example, where we start with some initialization of the library that will also provide the finalization. We keep our 2 dimensions, and then we create one of the data structures provided by Kokkos, a Kokkos view. Note that we have to pass some template parameters that I will detail later, but this is the equivalent of the sequential example. So we say here that we want a 2-dimensional array. We call the constructor of the class by passing some label and only the runtime dimension, because the compile time dimension is already known through the template parameters. And then instead of doing a sequential for loop, we call a function called parallel for. So this is quite similar to Sycl. You pass a label again, the number of iterations that you want to make, nx, so that mimics the sequential loop. And then you pass here, in this case, a lambda. So the lambda takes an integer as an input parameter, and that we use and that we pass in the function call operator of array. So instead of doing, as in the sequential example, a linearization by hand, we just use the function call operator that will do the linearization for us. So as you would do also in Fortran or Numpy. And with this version of it, we can run on CPU or GPU, depending on how we compile the code. So let's dive in more in detail into the Kokkos programming model. So the idea, as I said, is to write once and run anywhere. This is done by recompiling the code. So each time you want to, so you write your code once, and you recompile it to target a new architecture. So you get different binaries depending on the architecture that you target. Kokkos mimics and introduces a concept that mimics the hardware. So it is based on an abstract model for the hardware that you can have that you can see on the right. So an abstract node would be equipped with some memory that will be here in green, and that will be mimicked in the Kokkos model by memory spaces. and by also execution spaces that will mimic the execution resources that we can have on the node, either the cores or the accelerators in yellow. And as we have seen, it also provides some multidimensional arrays that are very important in scientific computing. To do the parallel work, Kokkos introduces some basic patterns. We have 3 patterns: parallel for, parallel reduce, and parallel scan. So the parallel for is just a parallelized loop where each iteration must be independent, and the user has the responsibility to avoid any data race in the function that is passed to the parallel for. So this is the same as the first example. The parallel reduce will allow you to, for example, do a sum over an array or any kind of operation. This changes a bit the signature of the function that you pass to Kokkos. So you still get an integer that will identify the loop iteration, but you also have a local reducer that is private to the thread calling the function that will have a local version of the reducer, and that will at the end contribute to a global variable that is passed as the final argument of the parallel reduce. And then you have also a less common pattern that is the parallel scan that is also sometimes called prefix algorithm or cumulative sum in Numpy, that will basically do, if you call a parallel scan over n, you will basically do n reductions. All these functions dispatch asynchronously, but they are sequential with respect to each other. So when, for example, the host calls the parallel for, it will launch a kernel, but it returns immediately. It doesn't wait for the result of the parallel for. And if again you launch a new parallel algorithm for example, the parallel reduce, it doesn't wait, but you are ensured that the 2 parallel algorithms are sequential with respect to each other. And if you need the host to wait for some results, you can call a barrier that is called in Kokkos fence to wait for the result. You can have a finer control over the way you launch the parallel algorithms that are called execution policies. We have 2 big families. The first one is the basic parallelism, which is then divided into 2 policies. The range policy that we already encountered, in fact, when we passed only n as an argument of the parallel for, it was a shortcut for this policy. And we have the ND range policy that will allow you to get multidimensional loops. So instead of getting only 1 integer, you can go to 8 dimensions, and you will get here as an input parameter the lambda 8 integers. So that can be useful, for example, for stencils. And it's also a tiled iteration space, and you can control the iteration order of each dimension. The second execution policy that I mentioned is the hierarchical parallelism. One thing that you cannot do with the previous one is to nest parallel fors. Once you have already launched a parallel for here, you cannot call a new parallel for inside, even though you could have some degree of parallelism available inside this parallel for. That is what allows you the hierarchical parallelism. So again, we call a parallel for, but instead of passing range policy or simple integer, you pass a team policy that will not get you an integer. It will get you a handle that is called team handle here. And then inside, you can call again a new parallel for, but this time by passing the team. So this matches the hierarchical structure of the hardware and the GPU, for example. You can also have access to a finer memory, like the scratch memory on GPUs, or what is called shared memory on CUDA. And at the inner levels, you have new execution policies, team thread, thread vector, and team vector that you can pass at the inner part. Again, you have either a one-dimensional or multi-dimensional range policy at the inner levels. And finally, regarding the execution part of Kokkos, Kokkos introduces the execution spaces that I mentioned earlier. For example, they will select the backend that you want to use. So for example, we have CUDA, heap, or Sycl for the device part, and for the host part, we have OpenMP or Serial. They are not all available at any time. So to be portable, we advise you to use some aliases that are predefined by Kokkos, and that will, depending on the compile options that you choose for Kokkos, be aliases to CUDA, heap, or Sycl. And if we take again the example of the range policy, instead of passing a begin, an end, and a chunk size, you can add the first parameter to pass the execution space instance. So here you could, for example, pass either default execution space to target, if you compile for GPU, to target a GPU, and default host execution space that will target CPU backend, even though you compile for GPU, if you want to ensure to run on the host. Now, regarding the memory aspect of Kokkos, Kokkos introduces the Kokkos view, which is the main container of Kokkos that is templated by different important parameters. So it's a multidimensional array, as you would have in Fortran or in Numpy. So the parameters are the data type, where the type of data that you want to store in memory. And Kokkos allows you to control also the layout that I will detail later, the memory space, where you want the data to reside, and some other aspects of the way you want to access the data. Regarding the copy semantics, it behaves like Numpy arrays, it's shared semantics. So if you call A equal B between two views, you will not overwrite, you will not have a deep copy. It behaves like a stud chat pointer, if you know. If you want really, if you really have two different allocations and you want a deep copy between the two, you have a dedicated function for that that is called deep copy. We have also some features to allow you to control mirrors between host and device if you want to pass data from the host and the device. And it's also, since recently, compatible with the NDSpan. That was actually kind of the first implementation of NDSpan. This is the Kokkos team that proposed the NDSpan to the standard library of C++. So I mentioned some template parameters. So one of them is the memory space. So this is how you choose where you want the data to reside. So when you are on the nodes of supercomputers, you have different memory spaces that are not all available from anywhere. So we want to control where the data resides. So Kokkos introduces some of them, the host space, CUDA space, or the UVM. And again, like for the execution spaces, to get some portability, we want to either use aliases or the memory space that are attached to the execution spaces. So we have the host space that is portable, but to get the default or preferred memory space of a given execution space, you can get it from the alias injected in the class. We have also shared space. That is the memory that you can access from anywhere, from the host and the device. And the scratch space that you want to allocate using hierarchical parallelism. Another aspect of the Kokkos views is the memory layout, which is an important aspect when you manipulate multidimensional arrays. That is how you interpret your one big array that is stored in memory. So Kokkos introduces 3 of them, the layout right, left, and stride. So they all follow this kind of formula. So if the I variables are the indices that you pass to the Kokkos view, so here in the case of 4-dimensional array, you pass I0 to I3. They all follow this kind of formula, but depending on the strong typing, this enforces different values for what we call the strides, here noted S. For the case of the layout right, this forces the last stride to be equal to 1. The case of the layout left, the first stride is 1. And for the layout stride, it can be anything. You typically get it when you take subviews of views. Kokkos is also more than that. It introduces other containers that I will not mention much. Offset views that are arrays that do not start at 0, like in Fortran. Dual views that will help you to manipulate data that is on the host and on the device. It contains 2 views, one that is always on the host and one that is on the device. And helpers, like if you want to synchronize the data between the host and device, it results to be no hope when you compile only for CPU, and there is an actual copy if you compile for GPU, for example. Scatter views that are algorithms related to the atomics, the SIND classes if you want to do some explicit vectorization. Regarding algorithms, recently we introduced some standard-like algorithms, so algorithms that are accelerated by the Kokkos implementations. Some sorting algorithm, random number generation, and also some helpers, less critical, but that can be quite useful. A printf that you can call from the GPU, the Kokkos numbers that are the stud numbers actually, and some also structures like pair or tuple that are actually really close to the standard implementation, but with the annotations that you need to generate functions for the GPU. That is for the Kokkos core, and Kokkos has also some ecosystem. So in this diagram, Kokkos is at the bottom, what I talked earlier. And on top of that, we have also other libraries. So for example, Kokkos kernels that will bring you some linear algebra features that you may need when you build a real application. That can also bring some ODE solvers, ordinary differential equation solvers. We worked on a portable Kokkos FFT, so that reuses the vendor libraries, but with a Kokkos View API. Other projects like Kokkos.com that will reduces the gap between distributed memory parallelism and Kokkos. Some Python binding. On top of that, we can build then real-world applications. We have some also tools that will help you to debug and profile the Kokkos applications, and we also do some support by improving the documentation, doing some trainings or communications like today. If you want further reading, I can advise you some of the articles that were published regarding Kokkos. We have, of course, the GitHub repository. We have a wiki for the official documentation. A few years ago, there was also a tutorial made by Christian Trott, the main developer of Kokkos, that is on YouTube. So as a conclusion, I hope I showed you that Kokkos can provide you some performance portability by abstracting the hardware. It's easy to adopt in C++ code base, and it's a quite active and widely supported project. And I would thank you for your attention. You have any question?
Maybe
Yes.
one very simple question. What are the main differences between Kokkos and Sycl for you?
For the core parts?
Yeah.
One main difference could be the dimensionality. We go higher than 3 dimensions. Sycl, I think, chose to be as close as possible to the hardware or to the backends like CUDA that supports only 3 dimensions. Kokkos will try to go higher. We have some applications that need higher dimensions. On the other hand, Sycl may have some more flexibility as it can allow you to choose at runtime where to run, whereas with Kokkos, you would do this choice at compile time. I think these are 2 differences that I can think of.
When did you start developing Kokkos?
Myself?
Well, where was Kokkos?
Kokkos started like 10 years ago now. Myself, I started like in 2017. I started my PhD. If you can read. We are almost releasing the version 1. In the coming months, it should be released. We support all the major backends of Kokkos. We support QFFT. So we use the backends, the vendor libraries, so QFFT for CUDA, HeapFFT for Heap, and the 1MKL for Sycl, and FFTW for the OpenMP and serial backends. All of them are supported. We don't have the support for less common backends in Kokkos like OpenMP offload and OpenACC. But feel free to, it's on GitHub and people are free to open issues if they have any.
And we do have another question on Discord from Adrien. I'm not sure to understand. Using Kokkos means that separate part of the same code can be compiled with different kind of parallelism, serial, CPU, and GPU, or do we need to choose between CPU and GPU at some point?
So you basically choose between default execution space and default host execution space in your source code. And then at compile time, you can choose whether you want to enable CUDA, Heap, or Sycl, or OpenMP. You cannot enable all of them at once. It doesn't make sense for Kokkos. So you typically choose at compile time one of the device available and one or two for the host. You can enable serial and OpenMP or threads, and one of the devices like CUDA, HEAP, or Sycl.
Thank you.
Just one point, because people may be confused seeing Kokkos using Sycl as backend, and now Sycl having backend towards other materials. So each portability layer sometimes use others as backends. So you have a pile of backends, but there in general, Sycl is used as a backend to the Intel GPU.
Yes, exactly.
That's why Kokkos use Sycl, just for the Intel GPUs.
Yeah, that's what Intel told the Kokkos team to use to target the Intel GPUs.
Yeah.
That's
why we have a portability layer using another portability layer.
Exactly. Actually, it's more I think, one API that we support. Not sure we have ever tested adaptive C++ for the Kokkos backend of Intel.
Another Discord question. How does Kokkos performance compare against CUDA on NVIDIA GPU?
It can add small overhead because there is some abstraction that is added on top of CUDA, but basically for 1D range policy, you get the performance that you would have with CUDA. The overhead is really minimal. You can notice some overhead with MD range policy that is known to have some performance issues, but this is also a work in progress. But other than that, the performance overhead is minimal.
Thank you.
Other questions?
On Discord, it's okay.
Okay.
So, Pierre is going to close.
Okay, that's all for today. And tomorrow we'll add some Rust on GPU with Vulkan. And then we'll have a talk on Julia also with Nabil. So see you tomorrow and bye.